Up. Oof. Today. My alarm went off, but I didn't hear it. And it just stops going off for some reason. But yeah, that's annoying, but it happens, I guess. It's quite preventable. Whatever. Get back into this. All right. Pretty slow start today. Reveal classes support static initialization. Yeah, that was a lot. So before CBP 11, objects required different types of initialization based on the type. Terminal types can be class objects can be motivated. Version. I was actually looking this up. Didn't initialize it. C++ is so much going on, bro. You can kind of imply that he says STD. He pronounces this as STD from saying and there. It's kind of interesting. Yeah, use parentheses, bro. Use static. Phrase initialization is not an expression. For example, float F2. Dude, this one is crazy. So the deduce type is standard in C++11. CPP 17. Let's change. Sorry for moaning into the mic. Change the rules for list initialization. Differentiating between direct and copy list initialization. New rules for type deduction. For copy list initialization, auto deduction, use it. The ill and ill form. Really? This is an error now. Huh. It's so. Sorry, dude. Yeah, I just got a weird cough thing. Let me So I think I'm gonna toggle back and forth between that kernel. This should be like a literal 12-hour stream, by the way.
Data
I'm gonna
type
switch through
of the
some of
container.
these
So in other words,
videos,
the
go
data
back to
type that
the
the container contains,
book,
that is
maybe
actually up to
hop
you to
on
decide. The
request
whole
a
thing's
bit.
made out of templates, which reminds me we need to talk about templates, and we will very soon. Templates are a huge topic, so we'll kind of divide it from beginning to advanced kind of templates as we go along. But essentially, all you need to know to use this, you don't need to know anything about templates to actually use the standard template library. All you need to know is that you can provide the underlying data type that this data structure actually handles. And that's pretty cool. It makes it very versatile, and it means that you don't have to resort to writing your own data structures or anything like that. So C++ provides us with a class called vector, and that vector is in the std namespace. Now, it's called vector. That's the first problem. Why is it called vector? Well, there's actually a story behind that. I've linked like an article or Wikipedia page in the description that will actually talk about that, but it shouldn't be called vector. It should be called something like array list, because that makes a lot more sense. It's essentially a dynamic or dynamic array, but not vector. Vector's a very weird name for this, and a lot of people who first kind of get into C++ really get confused about what on earth this vector thing is. Is it a mathematical vector? No. It's kind of like a set. It's a set that doesn't enforce any kind of uniqueness to its actual elements. So in other words, it's basically an array. But unlike the normal array types in C++, either just raw arrays or the standard array class, which we actually did mention in the arrays video. If you guys haven't seen that, click up there. But we will probably have a dedicated video about that as well. Unlike array, this can actually resize, which means that when you create this vector, when you create this dynamic array, it doesn't have a set size. You can give it a set size and whatever if you want to initialize it with a certain size, but you basically don't give it a size. You just create this vector or this array, and then you basically just put elements into it. And every time you put an element into it, the size grows. So I can start off not knowing how many elements I actually want in my array, and then just push 10 things into it, and suddenly I have an array with 10 items. Now, to people who kind of are new to programming or new to computer science, you might be like, well, how does that work? How is it possible to just have an array that resizes? And we're actually going to, over the course of this C++ series, we're actually going to be rewriting a lot of these data structures that exist in C++ ourselves. And in a lot of cases, we're actually going to optimize them and make them a lot faster than the ones in the standard template library, because the ones in the standard template library aren't especially fast. That's not really the priority of them. And so in a lot of cases, studios and teams end up actually creating their own container libraries. An example, I work at EA, so an example is we use something called EA STL. There's a link to that in the description below. It's on GitHub. You can look at the source code. That's one example of something that is actually usually, in most cases, a lot faster than the stuff that's actually in the standard template library. But anyway, I'm getting a little bit ahead of myself here. The point is that the way that standard vectors actually work, we'll talk about that in more detail in a future video. However, the gist of it is that basically when you exceed the size that it's allocated, so when you make a vector, it might allocate like 10 elements, for example, or enough memory for 10 elements. When you exceed that, it basically creates a new array in memory that's bigger than the first one, copies everything to there, and then deletes the old one. And that way you suddenly just have basically a new array that's somewhere else in memory that has a lot more storage, and you can keep adding things to it like that. In practice, it actually tends to allocate quite often and isn't the best performance-wise unless you set it up properly. So this video is just going to be for beginners who don't know what this vector thing is, how you can use it and all that. And then I think the next video after this one, we're actually going to talk about specifically how we can use the standard vector in an optimal way, and that'll kind of get into some more advanced things. So if you want to check that video out, if you already know how vector works and you want to waste your time watching this video, click on the link right there, and that will take you to the advanced, video, and we'll talk about how we can optimize our usage of the vector class. But for now, let's create a dynamic array. So what I've got over here is a basic struct here. That's the vertex. This is specifically a vertex position. I should add, as you can see, it's got X, Y, and Z. This is just a dummy class. It really could be anything. I've also written an output operator over here just so that we can print this easily to the console. If we were to make an actual static array of this, we would kind of have two choices, right? Ignoring the standard array class, we could just create a static array, which might have 5 elements in it, but this way we're kind of getting tied to the size. And even if we do allocate it on the heap, like so, you can see that we're kind of still tied to this size, and we've kind of allocated 5 vertices, which means that we can access 0 through 4. Again, if you're not sure how arrays work, definitely check out that video first. But we can access the index 0 through 4, and then if we try and go higher, we run into a problem. And sometimes that's just not good enough, because we want to keep adding vertices. For example, we might have a program where we allow the user to enter in data. We don't really want to stop the user after, I don't know, maybe 10 vertices or something and say, sorry, you can't enter anymore. If we want to keep that going, we need a way to say that when you reach that max capacity, resize, get bigger so that you can store more data. Another solution to this problem is kind of allocating an absurd amount of vertices and then basically just saying that's the hard limit for the program. Anything above that is ridiculous. We're never going to hit that anyway. So basically this program does support unlimited vertices in a way. But of course that's also not ideal because it means that you're using all of that memory, whereas if we only have 5 vertices, that's a huge waste. So what we can do instead is use the vector class. I'm going to include vector over here, and then we're going to go ahead and make one. So the way that we make one is we type in std vector, then we specify the type. Now this type is just a C++ type of what is actually going to be in the array. So in our case, we want to store vertices. So we'll type in vertex, and I'll call this vertices, just like that, and that's it, we're done. Now it's worth noting that unlike languages like Java, where you cannot pass primitive types in here, this is a C++ template, so you can pass primitive types in here. I can type int like this, or float like that. In Java, we would actually have to use the integer class or something like that, but this is very similar to C# as well, where we don't actually have to specify the class type, we can just specify the raw type, the primitive type. So I'm going to change this back to vertex. Now note that I'm not storing a bunch of pointers to the vertex structs, right? I'm actually just storing vertices, just vertex, just inline. And there's actually a big difference between that. A lot of people tend to ask, should I be storing pointers to heap allocated classes in my vector, or should I be storing just stack allocated, basically inline allocated, like vertex classes or vertex structs? And the answer to that is, it depends. It really does depend. I think I'm going to make a video in the future that will talk about this specific problem in more detail, because for a lot of people, it is hard to decide whether you should be using like vertex pointers in this case, or just vertex objects, right? There's a big difference. The primary consideration is that it is technically more optimal to store vertex objects instead of pointers, because if you store vertex objects, your memory is going to be inline. Dynamic arrays are arrays in the sense that their memory is contiguous, which means that it's not fragmented in memory, right? It's all just in a row. And if you store vertex objects inline like this, you've literally got one vertex XYZ, 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 one after the other. And that's really, really optimal if you actually want to iterate over them and set all of them, or change all of them, or read all of them, or whatever it is that you want to do with them, because they're likely going to, well, they are all going to be on the same cache line in that sense. I know I said beginner, and I'm already talking about cache lines and stuff. We're going to get into this in the future, but basically, you want to try, if it's at all possible, try and allocate them inline like this. The only problem with this is that if it comes time to actually resize the vector, it needs to copy all that data. And if you happen to have something like a vector of strings, and you're going to be resizing that vector often, and it does need to reallocate and recopy everything, that could potentially be a very slow operation. Whereas with pointers, the actual memory stays intact because you're just holding pointers to that memory, right? So the actual memory stays intact, but then when it comes time to resize, it just copies those integers, which are the memory addresses, to the actual data, and the data is still stored just in various places in memory. So it is a bit of a hard decision, and I don't really want to get into it too much now, but that should just give you kind of the gist of this. Try and keep them as objects if possible. Pointers are kind of always, as with stack allocation and heap allocation, pointers are always kind of your last resort if you really need to actually do it that way. So now that I've got this, how do I add stuff to it? Well, it's very simple. You just type in vertices.pushback. In other languages, it's called add or add. In C++, the same operation is called pushback, and then you basically push back a vertex. So in this case, I don't have a constructor, but I could just use an initializer list like this to specify my x, y, and z. So I'll say 1, 2, 3, and then I'll push another one back, and we'll write 4, 5, 6. Okay, pretty basic stuff. Now let's iterate through all these and print them. So in an array, we don't know, or I should say in a C-style array, we don't actually know the size of the array. But in this case, of course, since vector is a full class and everything, we actually do know the size, and we can ask it. So let's write a for loop, and we'll write I is less than vertices.size. That's the function that we use for retrieving the size. And then I'll just say std_cout vertices, and then we can use the index operator to access. In Java, we have to use .get, because Java, of course, doesn't have operator overloading, but C++, very much like C#, has overloaded the index operator so that we can actually just type it in like that, as if it was just any array, which is nice. So if we hit F5 now to run our code, you can see that we get 1, 2, 3, 4, 5, 6, which is perfect. We can also use range-based for loops with this. So instead of writing all this code, we could rewrite this for loop like this, which is going to look much simpler. We'll just say for vertex v, then colon, then the name of the vector, which is vertices. We can just print v like this. And if we hit F5, you can see that we get the exact same result printed twice. Now in this specific example, because I've written vertex like this is actually going to be copying each vertex into the scope of this for loop. We don't want to do that. We want to avoid copying wherever possible. So if we just stick a simple ampersand over here like this, or maybe even mark it as const, it doesn't really matter. As long as you've got the ampersand here to make it a reference, it's not going to copy the data. And if we run this, we will get the same result. However, we're not just needlessly copying vertices. Finally, if we want to clear the list of vertices, we just type in vertices.clear. That will set the array size back to 0. We can also remove vertices individually just by doing vertices.erase. And then with this, now I love C++ because of this. Look at this. To someone who's new to C++, looking at this actual function signature, it's like, what is going on? And even me right now reading this after so many years, it's like, what's up? I know this is why a lot of people hate C++, not very beginner friendly, but if we read this, it does make sense. Arrays returns a vector iterator, so we can kind of just ignore all that return type. This is the arrays function. Then over here you can see takes a const iterator. Okay? What that means is that we can't just write arrays2 or something like that. We actually have to take in an iterator. Now if we want to specifically remove, for example, the second element, which is at index 1, what we can actually do is take in the beginning of vertices by typing in vertices.begin and then just add 1 to it. And then that will actually erase that second element. So if we move this for loop down here after the erase to see what happens, you can see in this case, we do actually erase that second element and everything's great. Another thing that I'll mention is that when you are actually passing these vectors into functions or into classes or whatever, you really do want to make sure that you're passing them by reference, okay? If you're not going to be modifying it, then by const reference, just like this. Because by doing that, you're ensuring you're not copying that entire array into this function. So make sure that when you do stuff like this, you actually do pass it by reference like that, okay? Very important stuff. Okay, I think that's pretty much it for a basic overview of the vector class of dynamic arrays in C++ and how you can use them. In the next video, we're going to really get in depth and talk about optimization, about how we can avoid reallocations, how we can avoid copying and all that stuff, and probably some other tips and tricks with vectors in general for people who already kind of get the general premise and want. Hey, what's up guys? My name is Acherno and welcome back to my C++ series. Last time we talked about dynamic arrays in C++ and specifically the vector class. If you guys haven't seen that video, definitely check that out first. That's going to cover the basics of what a dynamic array actually is and how to use the vector class in C++. And this video here It's going to show you how you might use that vector class in a more optimal way, a little bit about how it works, and just in general how we can write our code so that it just runs faster. This is kind of exciting because this is like our first kind of optimization video, and over the course of this series we are going to be talking a lot more about optimization because C++ is specifically a language which plays nicely with optimization. It's a language that many people pick due to the fact that they might need some lower level optimization. And one of the most important rules of optimization is basically knowing your environment. And what I mean by knowing your environment is how do things work and what do I need to do exactly? And what should happen, right? And that's such a complex topic in itself that we are going to dive deeper into it as the series goes on. But for today, we're just going to scratch the surface and take a look at what we can do specifically with the example of vector. So to optimize your vector usage, you really should know how vector works and how you can maybe change it to work a little bit better. So basically the way that the standard vector class actually works is you create a vector and then you start pushing back elements. And when you add elements into that array, into that vector, if the size of the vector, if the capacity of the vector is not large enough to contain this new element that you're trying to add, basically what needs to happen is the vector needs to allocate new memory that is at least large enough to hold this new element you're trying to add, as well as the current contents of the vector, and copy everything across from that old location in memory into the new location in memory, and then delete that old location. That's what happens. And so when we try and push back an element, if the capacity runs out, it performs that resizing, that reallocation. And that specifically is one cause of kind of slow code. It's the fact that if we continually need to reallocate, that's a slow operation. We need to reallocate when we need to copy all of our existing elements. That's something we want to avoid. And in fact, that's going to largely be our optimization strategy today. Copying. How can we avoid copying our objects if we're dealing with vectors? And specifically dealing with object-based vectors. So we're not storing a vector of pointers, we're actually storing a vector of objects. Now, I've said that knowing your environment is one of the most important things with optimization. And right now we're trying to optimize for copying, so we need to know when copies actually happen and why they happen. Let's take a look at some code and figure that out. So from the last video, I had this vertex class, I just added a constructor to it, but we basically have this kind of default code. It's pretty simple. We have our two vertices that we're pushing back, nothing too fancy. Now let's take a look at what actually happens behind the scenes and identify how many, if any, copies are actually happening with this current code. So a good way to do that is to add a copy constructor to vertex and maybe either put a breakpoint in there or just print something to the console to see when that copy constructor actually gets called. So what I'm going to do is just write a copy constructor. If you're not sure what a copy constructor is or how copying actually works in C++, then definitely check out the video that's linked in the top right corner. But I'm just going to write a very, very simple copy constructor for this vertex class. Now for the purposes of this, we don't really need to fill it out properly, but I've done so anyway. What I'm going to do is print copied over here to our console so that we can take a look at that, and let's run this code. Okay, so we get 3 copies. Interesting. I'm actually going to add another element here, and this time, since I can, I'm just going to use the actual constructor just so that this code looks a bit easier to read. So I'll make this 7, 8, 9, and in fact I'm going to switch over my existing ones as well to use this kind of new constructor that I've made. This is just the original default constructor. It does exactly the same thing as the code before, but I think it might just be a little bit easier to read because you know exactly what's happening. Okay, so if I run this code, how many copies do we expect? 6. We have 6 copies. Now you might be asking yourself, why? Why is that happening? Why is C++ copying my vertex 6 times in total? What's going on? To debug this a little bit further, I'm going to place a breakpoint on this line and run this code again. So we have 0 copies at the moment, of course, because we haven't even pushed anything back. Let's hit F10. So now we've pushed one element back, one vertex, and we have a copy. Right? Why is that happening? The reason that's happening is because when we construct our vertex, we're actually constructing it in the current stack frame of the main function. So we're constructing it on the stack in main. And then what needs to happen is we need to put it into that vector, right? So we need to somehow get it from that main class, from the main function, rather not class, function, from the main function into the actual vector, into the memory that the vector has allocated. And of course, the way that we do that is we copy it from the main function into the vector class. That's our first kind of mistake. That's the first thing we can optimize. What if we could just construct that vertex in place in the actual memory that the vector has actually allocated for us? That's optimization strategy number 1, which we'll implement in a second, but let's keep going. Now, if I hit F10 over here, we get 2 more copies. So we're now at 3 copies. Right? So we already know what's happened. We already know where one of the copies has gone. It's because we're constructing this vertex object inside the main function, then pushing it into the vertices vector, which causes a copy. But then why are we getting an additional copy? What's going on? Well, if we hover our mouse over this and we take a look at the actual vertices vector, we can see the capacity is 2. What that means is that this vector physically has enough memory to store 2 vertices or 2 vertex objects. So what happens, of course, is when we try and push another one on, like this third one, and I hit F10, it needs to resize the capacity to 3, or to anything higher than 2 basically, so that we can actually have enough memory to push in our third vertex. So that's another potential optimization strategy. Our vector is being resized twice here. It's at 1 by default, it then moves to 2 when we add the second element, and then moves to 3 when we add the third element. If we know our environment, if we know that we are planning to push in 3 vertex objects, why don't we just tell the vector, hey, make enough memory for 3, so that you don't have to resize yourself twice. Just make enough memory from 3 from the beginning, because I plan to actually push in 3 elements. That's optimization strategy number 2, which we'll implement in a minute as well. So that is the idea of where these 6 copies are coming from. So let's do the quick and easy optimization strategy, I guess. Let's just tell the vector, hey, I want you to please have the capacity of 3. And the way that we can tell the vector, I want to have the capacity of 3, is by simply, after we create it, setting vertices.reserve 3, and you can see that takes in a capacity. Now this is different to resize, or if we were to pass in 3 in the constructor. If we actually try and pass in 3 in the constructor, this code won't even compile. And you can see if I just move this up, the error that we're getting is vertex no appropriate default constructor available, because what this will actually do is not just allocate enough memory to store 3 vertices, or 3 vertex objects, it's actually going to construct 3 vertex objects. We don't want to construct any objects yet, we just want to have enough memory to hold them. That's what reserve does. Reserve makes sure that we actually have enough memory. So the first step is we create this vertices vector, and then we reserve 3, and then we push back our elements. Let's take a look at how many copies we now get with the addition of this one line of code. Look at that, 3 copies instead of 6. that's half as many copies. And of course, this kind of goes up exponentially. If we add 10, that's going to be a lot more copies. So we've saved a great deal of copies already. So this is great, but we can do better. We're still getting a copy because this vertex is actually being constructed over here inside the main function and then copied into the actual vector. I would like to just construct it in the actual vector. And the way that we can do that is by using emplaceBack instead of pushback. And so in this case, instead of actually passing a vertex object that we've constructed, we instead just pass the parameter list for the constructor, which basically tells the vector, hey, construct a vertex object with the following parameters in place in our actual vector memory. So I'll do that for all of these. And we'll replace pushback with emplaceBack. Let's hit F5. Look at that. Clean. Clean as a whistle. That is a nice looking console output. Not a single copy in this code anymore. Do you see how we've just optimized this really easily by just knowing how it works and being aware of the fact that our vertex object was actually getting copied like 6 times? It's not even hard to write code, but this code over here specifically is going to run a lot faster than the code that we originally had, and it didn't even take long to optimize. It's just about knowing what's actually going on, knowing our environment, and knowing how we can actually optimize using the tools that we have available. Anyway, I hope you guys enjoyed this video. This is like our first kind of introduction to optimization. I love talking about this stuff, so we are going to be talking a lot more.
Move on to look
Hey, what's up guys, my name is Eternal and welcome back to my C++ series. Over the last couple of episodes we took a look at what the static keyword meant in certain contexts, and today we're going to have a look at one other context that you might find the static keyword in, and that is in a local scope. So you can actually use static in a local scope to declare a variable, and that has a bit of a different meaning than the other two statics that we've looked at. And the idea behind this meaning makes a lot more sense if you think about the two kind of considerations that we have to make when we're declaring a variable, and that is the lifetime of the variable and the scope of the variable. The lifetime refers to how long that variable will actually stick around for. In other words, how long it will remain in our memory before it gets deleted. And then the scope refers to where we can actually access that variable. So of course, if we declare a variable inside a function, for example, we can't just access it in another function because the variable we've declared is going to be local to the function we declared it in. So a static local variable allows us to declare a variable that has the lifetime of essentially our entire program. However, its scope is limited to be inside that function. And it really has nothing to do with functions in particular. I mean, you can declare this in any scope really. I'm just using function as an example. It's not really just limited to being inside a function. It could be inside an if statement, could be anywhere. Which is why, again, there's not much of a difference between static in a function scope versus static in a class scope, because the lifetime is actually going to be the same. The only difference is that the one in the class scope, anything in the class can access it. Anything that is inside that class scope can access that static variable. However, of course, if you declare one inside a function scope, it's going to be local to that function instead of being local to that class. Let's jump in and take a look at some examples. So the simplest example is going to be just to create a function and then declare some kind of static variable inside it. So I'll just make static int I equals 0. What this means is that when I call function for the first time, this variable will be initialized to 0, and then on subsequent calls to functions, it's not actually going to create a brand new variable. Really easy way to check this out is if I just print the value of I, and then I increment it every time I call the function. So if we didn't have static here, what you would expect is that every time you call this function, I get set to 0, then I gets incremented to 1, and then I get set to 0, then I gets incremented to 1, and then we print 1 to the console. And in fact, we can test that out by just calling function a whole bunch of I get set to 0, then I static here. What you would expect is that every time you call this function, I get set to 0, then I gets incremented to 1, and then we print 1 to the console. And in fact, we can test that out by just calling function a whole bunch of times here. We'll call it 5 times. We'll hit F5 to run our program. And you can see that we get 1 printing 5 times because, as I just explained, we create a variable every single time and we set it equal to 0, we then increment it to 1, and then we print that to the console. Now, if we were to make this static, then it's very, very similar to if we had just moved this original declaration out here. So if we run this code, and it doesn't really matter if this has static or not, in our case it's going to be the same. If you want to know more about what static does in that sense, you can check out the video that's linked somewhere. So if I run this code, you would expect I to be 0, incremented 5 times, and so you'll get 1, 2, 3, 4, 5, which is exactly what you get. However, the problem with this approach is that I can access I anywhere. I could set I equal to 10 over here in between function calls, and suddenly this dramatically changes what my program does. So for cases where you want this kind of behavior, however, you do not want to give everyone access to that variable, you can declare static in a local scope. So let's get rid of this and move our I variable back into the function scope. I'm going to stick static out the front, which means that, again, the first time we run this function, it's going to set it equal to 0 and create the variable in the first place. Then on subsequent times, it's just going to refer to that original variable. So if I run my code now, you can see I get 1, 2, 3, 4, 5, and I get the exact same behavior as I did before. However, that I variable isn't visible in a global scope. It's just local to that function. Now, as for uses, some people do like to discourage the use of this because of certain reasons that I don't fully understand, because I don't really see a problem with this. It definitely has its use. It's one of those things where, yes, you can achieve the exact same behavior using other methods. However, that can also be said for classes. You don't necessarily have to use classes at all to write a program. However, it does make your life easier. Same with this case. It's one of those things that you can just do to keep your code a little bit cleaner. Another example might be if you had a singleton class. So a singleton class is a class that should only have one instance in existence. If I wanted to create this singleton class without using this static local scope thing, I would have to create some kind of static singleton instance, probably a pointer at this rate. I'll set it here. I would have to have if I just wanted to return a normal reference, I would have to have a singleton reference returning get function, which was static and returned my instance after dereferencing it, of course. I would then have to actually declare this instance over here. Singleton, s instance. And we can probably set it equal to null pointer as a default. And now I have the ability, let's get rid of this. Now, of course, I have my singleton class in which I can just call singleton get and then do whatever I want with it. So suppose we had a method here called hello. Don't really know what I'm doing, just an example. We could call that hello method and everything will be well. You can see we've only got one instance of that class that we can use, so we can kind of use it statically. Now, this is quite a lot of code. You don't necessarily have to do it this way. Another way to do this with our newfound knowledge of this local static thing might be like this. We can get rid of this entirely, we can get rid of this external definition of sinstance as well. And then we can just expand our get function to actually create a static singleton instance and then return that instance. And there you go. We get the exact same behavior. You can see everything here stays the same. We can run our code no problem. Of course, the code's not actually going to do anything at this point, but you can see it runs successfully without crashing, and we don't really have any problems with this at all. And you can see that our code is a lot cleaner. Now, of course, if you didn't have the static keyword here, then this singleton, since it is just created on the stack, would get destroyed as soon as you hit this curly bracket, and then the function scope ends. So this would be a grave error, especially if you're returning it by reference. If you're copying it, of course, you wouldn't really have a problem. However, since we are returning a reference to it, this would be a huge problem. However, by adding static, we're extending the lifetime of this to be essentially forever, which means that every time we call get, the first time it will actually construct that singleton instance, and then on all subsequent times, it will just return that existing instance. So this is a great example of where you might want to use something like this. It doesn't necessarily have to be with singletons. It can help you out a lot by replacing initialization functions, where, for example, you might have to call a static initialization function at some point in your program to create all of your objects, so that you can actually use the static get methods and stuff like that. You can just kind of simplify that by using this in a lot of cases. So you can see there are tons of uses for this, and it's really not all that bad, so feel free to use it. That's my opinion. Let me know what you guys think of this static in a local scope thing in the comments below, and I'll see you guys in the next video. Goodbye.
Right, back to this. Kind of on topic. Characters replaces with static class. Many developers prefer assignments in the constructor body. Aside from the several exceptional cases, actually not to be done in the initializer list, or as of C++11, using default memory initialization. Prior to C++11, constants and non-constant non-static data members of the class had to be initialized. Initialization on declaration in a class was not possible. We'll see here this limitation. For the default member initialization. Initialize non-static members of a class. You could use default member initialization for constants. Okay. Use default member initialization to provide default values for members of classes with multiple vectors. I would use a common initializer for that. Okay. Use the constructor initializer list to initialize members that don't have default values but depend on constructor parameters. Like text. And these. Use assignment in constructors when the other options are not possible. Initializing data members with the pointer this. Second constructor parameter values. Throwing exceptions prior to initializing member values. Yeah, use this when possible. Because I think it limits a copy, yeah. That is important to note. They're destroyed is the destruction. The default constructor. Got the text constructor. Got a copy constructor. Got a move constructor. You got an assignment. Got a destructor. Are the two wraps of this. Constructor. Constructor again. Assignment destructor. You thought copy. Right. CPP11. Non-static data members can be initialized when declared in the class. This is called default member initialization because it is supposed to represent it. Default member initialization is intended for constants that are not initialized. These. Like these. But what is this called again when you do this? This is called initializer list action. Text flow. Non-constant, non-static, that does not depend on the way it's initialized. Also use default member initial. Text is also non-constant, non-static, but its initial value depends on how it's constructed, so you do it. Initialize it. The data member is initialized both the member initialization and constructor initializer list. The latter takes preference. The default value. To exemplify this, let's again consider the foo class and the bar class. You got a bar. So it's kind of hard to read this. There's a little left and then right. How does it do that? kind of weird. You're making a Barbie. Make a Barbie. Bars. I think I got cut off. Open. Or no, this is a constructor for bar. Okay, so then you make a Barbie. Bar with B. This B. You're just constructing it. Be the constructor initializer. Controlling and querying object alignment. So, I'm guessing it's gonna be talking about the arrow. So I've never seen align this. Let's go back to a video.
Hey, what's up guys? My name is Eterno and welcome back to my C++ series. First of all, haircut. Second of all, today we're going to be talking all about libraries in C++ and specifically how we can use external libraries in our project. So if you're used to other languages such as Java or C# or Python or something like that, adding libraries is a pretty trivial task. You might be using a package manager, you might not be, but either way, it's usually pretty straightforward. When it comes to C++, everyone seems to have problems. And back in the day, I had issues with this as well, and I don't even know why. It's actually really simple, and hopefully this video will kind of help clear it up for you. But basically, there are a few strategies that we can actually take when we're dealing with libraries in C++, and I'm going to kind of show you my way, as well as maybe discuss some of the other ones. But first of all, I hate the idea of package managers, and I hate the idea of linking to kind of other repositories or all of that stuff. My ideal project setup is that if you check out my repository, my code repository from GitHub or whatever, you should have everything you need in that repository just straight away for you to actually be able to compile and run the application or the project or whatever, right? There should be no kind of syncing up with package managers, downloading other libraries, all of that stuff. I hate all of that. I just, especially with C++, there are some package managers for other kind of languages, which makes sense. I'm specifically obviously talking about C++. This is the C++ series, but for C++, I just want stuff to work. I just want to be able to clone the repository and I want it to compile and run. So for that reason, I tend to actually keep versions of my dependencies, of the libraries that I'm using, in the actual solution, in the actual project folder. So I've actually got copies of those physical binaries or code, depending on which way I go with that as well, in my actual kind of working directory of my solution. That kind of brings me to another point. Should I be compiling these myself, or should I just be linking against pre-built binaries? Now, for most serious projects, I would absolutely recommend actually building the source code. If you're using Visual Studio, you can just add another project which contains your kind of source code of your dependency of your library, and then compile that into either a static or dynamic library. However, if you don't have access to the source code, or if you're kind of just, this is a quick project, I don't want to spend time setting this up because it's kind of a throwaway thing, or it's just it's nothing serious, then I would probably link against the binaries because it's just going to be quicker and easier. So today specifically, we're going to be linking against binaries. We're not going to be grabbing the source code of an actual kind of dependency of an actual library and compiling it ourselves. I might save that for another video. If you're interested in that, let me know in the comment below. But today, we're just going to be dealing with binaries. And specifically, what we're going to be dealing with is a library called GLFW. Now, my OpenGL series, which is all about OpenGL and graphics programming and stuff like that, in episode 2, which I've linked up there as well, we actually did download GLFW and link it, so you can take a look at that if you like. Maybe I show some extra things there, but today we're actually going to go through it slowly and take a look at everything. But if you kind of want to see it in a context of a real application, then check that series out. Another thing to note is that binaries might not be available for your actual project, right? For your actual library that you want to link. So you may actually be forced to build it yourself. This is especially true with like Mac and Linux, because for Unix systems, people usually just love building code. For Windows, a lot of people who use Windows just want stuff to work. Like me, I just want things to work. So that's why pre-built binaries exist. And again, I'm just saying that in a more kind of professional, larger project, in a space where I actually had time, I would for sure compile it myself because it helps with debugging. It helps with if you want to modify the library and change it a little bit. I do that quite frequently. I just love having the source code right there in the Visual Studio solution. But today, let's talk about binaries. So over here we have glfw.org, which is the GLFW website. There are a few downloads here. If you click this download button, it will download the source code for GLFW. But instead, we're going to go to download, and you can see that we have pre-compiled binaries for Windows. Another great example here. You can see for Linux and Mac OS, you have to compile it yourself. But for Windows, we have these binaries. binaries. Now, this brings us to our first question. Do I want 32-bit binaries or 64-bit binaries? This has nothing to do with your actual operating system. If you're running Windows 10 64-bit like I am, that doesn't mean that you should be grabbing the 64-bit binaries. What that means, or like the way that you choose the ones you want, is for your target, for your application target. So if I'm compiling my application as an x86 application, as a Win32 application, then I would want the 32-bit binaries. If I'm compiling a 64-bit application, I want 64-bit binaries. Make sure you match them together, because if you don't, they won't link. So in this case, I'm going to just be making a 32-bit application, so I'm going to grab the 32-bit Windows binaries and download them. Once I've downloaded and extracted them, we'll have this folder over here. Inside there, we have a bunch of folders and some other text files. And this is kind of the typical layout, I guess, or the typical organizational structure that we have with libraries in C++. There are two parts to a library usually. Includes and libraries, right? So an include kind of directory and a library directory, or a lib directory. So what the include directory is a bunch of header files. If you don't know how linking works in C++, or what I even mean by linking, check out the How C++ Linker Works video that I've made in the top right corner there. It covers this stuff in depth. But basically, the include directory has a bunch of header files that we need to use so that we can actually use functions that are in the pre-built binaries, and then the lib directory has those pre-built binaries. And there are usually two phases to this, right? There's usually dynamic libraries and static libraries. Not all libraries actually not all libraries supply both of them for you. GLFW does though, and you can choose if you want to link statically or dynamically. We're going to talk a lot about the differences between static and dynamic linking in another video specifically about that, but I'll cover the differences for you kind of simply here. Static linking means that the library actually gets basically put into your executable. So just it's inside your .exe file or whatever your executable is for your operating system. Whereas a dynamic library gets actually linked at runtime. So you still do have some kind of linkage. You can choose to load a dynamic library kind of just on the fly. Literally, there's a function called load library, which you can use in the Windows API as an example. And that will load you like your dynamic library, and you can pull function pointers out of that and start calling functions that way. But you can also have a kind of, at the application launch, it loads your .dll file, which is your dynamic link library. Again, we're not going to talk too much in depth about this, but there's just that difference of whether or not your library actually gets compiled into your exe file or linked into your exe file, and actually having a separate file for your library at runtime, which you need to have alongside your exe file or just somewhere so that your exe file can actually load that. Different stuff. Because of that kind of dependency of you now need to have a DLL file as well as your exe file, usually I like to go for static linking whenever possible. Static linking is also technically faster because the compiler or the link can actually perform kind of link time optimization and all of that stuff. Linking statically can technically result in a faster application because there are several optimizations that can be applied since we actually know the function that we're linking kind of at link time, whereas with dynamic libraries, we don't know what's going to happen. We have to leave it intact. And when the library actually gets loaded by our application at runtime, that's when the paths kind of get patched up. So usually static linking is the way to go. But for this video, I'm going to demonstrate both of those strategies. So again, we have the include files and then we have the library files, two kind of components that we need to set up. So for our compiler in our Visual Studio project, we have to point it to the header files, to the include files, so that we actually know which functions we have available to us, and so that we have those function declarations. Really, they're symbol declarations because they could also be variables. I'm just using functions as an example. And then we also have to point our linker to the library files. And I'm waving my hands around a lot, but that's just how I talk, so deal with it. And then we also need to tell our linker, this is my library file. I want you to link this so that we actually get the function definitions linked correctly. Let's go ahead and do that for both static and dynamic libraries. So I've got this Hello World project here in Visual Studio. It's very basic stuff, but what I'm actually going to do is inside the solution directory, make a folder called dependencies. This is how I actually manage my dependencies and my libraries. Inside dependencies, I'll make another folder called GLFW, and inside there, I'm going to put the files that I actually downloaded, which are the GLFW library. So include and libvc 2015. You can see here that they've actually appended kind of which compiler they used to actually compile this library file. So MinGW, MinGW64, and then basically all these versions of Visual Studio. We'll just pick the latest one. It doesn't really matter at the end of the day. They are just kind of compiled binaries, and they will work with kind of either one, but we want to use the one that's most compatible with our current toolchain, which is VC 2015, because we're using Visual Studio 2017. So I'll copy that and the include into this folder here. Include, you can see, has a GLFW folder and then a bunch of header files. Perfect. And lib has 3 files for us. GLFW3.dll is the runtime kind of dynamic link library that we actually use if we're linking dynamically at runtime. And GLFW3.dll.lib is actually kind of the static library that we use with the DLL so that we don't have to actually ask the DLL, hey, can I please have a bunch of function pointers to all of these functions? The idea is that this lib file actually contains all of the locations of the functions and symbols inside GLFW3.dll so that we can actually link against them at compile time. So in comparison, if we didn't have this lib file, we could still use this stuff. However, we'd have to ask the DLL file for each function by name and actually be like, hey, I want GLFW init or whatever. But this lib file already kind of contains all of those locations for us, so the linker can just link to them immediately. GLFW3.lib, which you can see is significantly bigger than the other ones, is the static library. So this is what we link if we don't want compile time linking, and if we do that, we don't need this DLL file to be with our exe file at runtime. Okay, cool. So let's actually link this stuff. I'm going to right-click on my Hello World project, hit Properties, and the first thing I'll actually do, I'll go to C++, General, and then in Additional Include Directories, I'm going to specify my Additional Include directory. Now, note your configuration and platform. Make sure you're editing the right ones. I obviously want this to apply for all configurations, so I'll just hit all configurations. Now, the include directory is the actual directory that goes into this include folder. So that's it. I could just copy this directory, but obviously you can see that it's in C, users, yarn documents, very specific to my computer. If someone ends up cloning this from GitHub or something like that, they're not going to have this path and their code isn't going to compile. What I actually want to do is have a path that is relative to this actual directory. So Hello World is the directory with my solution, right? Everyone's going to have that if they check out my repository, because this is my repository. So starting from this solution file, which I can do by typing in solution dir. This is a macro that you can use in Visual Studio. If I go under here into edit, you can see that it actually evaluates to this value, which is the solution directory. If I hit macros over here, I can see all of my macros, and I can type in like solution dir as an example, and you can see what it is. There's also things like project directory, which is the directory of the project. You can see that it's inside another Hello World folder, but the one that we care about is solution directory. So we'll start off there, and then we'll basically get that relative path, which in this case is dependencies, glfw, and include. So I can just grab there's no difference because quotes will actually check your relative paths first, and if it doesn't find anything relative. Now, I haven't actually linked against the libraries at all. So I've told the compiler that, hey, there's a bunch of functions. If I go to glw3.h, you'll actually see that there's a bunch of stuff here. I have a function, for example, called glfw_init. So let's try calling this. Over here in my code, I'll type in int a or something equals glfw_init. I don't know why my curly brackets are black. That is the worst idea ever. I'm gonna fix that after this video. Anyway, you can see that if I do glfw_init like this, it looks like everything's fine. I can hit Control F7 to compile my code. You can see I don't get any compile errors. But of course, if I try and actually build my project and run it, I'll just hit build. It's not gonna link correctly, and you'll get an error here that says unresolved external symbol, glfw_init. This is the cause of so many problems for people. What this means is that you haven't linked your actual library. The linker can't find this glfw_init function. If we actually go to the header file again and we take a look, it's just got a semicolon here. This doesn't tell us what the function actually does, it just tells us that the function exists. What we need to do is actually find a definition for that function. Now, we could provide one. I'm showing you this so that you know how it works. So we know that glfw_init takes no parameters and returns an integer. I could literally write glfw_init here and just like return 0 or something like that. And then now if I build this and compile it, you can see that it is going to successfully generate my hello world.exe file, and the build will succeed, because I'm actually providing a definition for this function. Now obviously we don't want this definition, we want the one that's actually in the library, so we need to link against the library. Hopefully that clears things up. So I'll right click on hello world, hit properties, make sure again I'm in all configurations and on the right platform, go to linker, and then general. Now, inside linker input is where I actually want to include that glfw3.lib file, right? I actually want to include it over here. However, I don't want to have to specify the entire path. So again, I could do like, solution directory / blah, blah, blah. I just want to keep this clean and just have glfw3.lib here. So if I want to do that, I actually need to go back to general and set my additional library directory, just like I did in C++ general with my additional include directory. So this should be the root directory, which contains my glfw3.lib library file. So again, I'll go over here into my glfw folder, go back here to lib, and then this is the directory I care about. So I'm going to grab this and copy it. And then I'm going to come back to additional library directories, type in solution dir, and then paste in that path just like that. Okay, so I've specified a library directory, and then I've also specified the name of a library file that is relative to that library directory. So if I hit OK, and I try and build this now, you can see that this works fine, and we don't actually get any errors. And if I was to, for example, run this, let's just print the result of this to the console, hit F5, you can see that we actually get one printing here, which basically means that glfw initialized successfully, so everything's working fine. Now, similarly to how I showed you how I actually manually added a glfw_init function definition, the same kind of applies for a header file, right? If I get rid of this include, or I don't have my header files, I just don't know that there's a function called glfw_init actually available. If I try and compile this code, it's not that it's not going to link, it's just not going to compile, because there is no such function. The compiler can't see a function called glfw_init. However, if I provide the actual declaration here by typing in glfw_init and just returning nothing like that, and hit F5 to run my code, the idea of this will actually work. However, in this specific case, we get an error because glfw is actually a C library, and what we're doing here is mangling the name with C++. I'll have a video specifically about kind of using C with C++ and name mangling and actually what's going on here, but to cut this short, we need to actually add extern C to this function declaration, which basically just says that preserve this name as it is because you'll be linking against a library that was built in C. So now if we compile this code, you can see that it works successfully. And if I run it as well, we still get one. Same result that we got when we had the header file. So just remember, those header files are kind of just there so that you don't have to do this stuff yourself. It's not like the library linking is magic or includes a magic or anything like that. It's just all components of a system that kind of go together. So the header files kind of just tell us which functions we have available by providing us with declarations, and then that library file provides us with definitions so that we actually can link to those functions and execute the appropriate code when we call the functions in our C++ code. Okay, I'm gonna wrap up the video there. I know we didn't talk about dynamic libraries, but this video's just been trailing on. I actually thought. Hey, what's up guys? My name is Echeno, welcome back to my C++ series. So last time we talked about how you can actually use libraries in C++ in your C++ project, and specifically how you can link them statically. But today we're going to be talking all about dynamic linking, what it is, how to use it, when you should be using it, and all that stuff. And this time we're going to be linking glfw dynamically. So in the static video we linked it statically, and now we're going to link it dynamically and kind of see what's involved in that and what the differences are. So first of all, dynamic linking. What does it mean? How is it different than static? Why is it called dynamic? So dynamic linking is linking that happens at runtime. So static linking happens at compile time. When you compile a static library, you then link it into either an executable, an application, or a dynamic library. And that's kind of it. You're done. You literally take the contents of that static library and you put it into, like, with the rest of the binary data that's actually in your dynamic library or inside your executable. And because of that, there are a number of optimizations that can happen because the compiler and the linker is now fully aware of the code that actually goes into an application when you link statically. We're going to be talking more about the actual performance differences and what linking statically versus dynamic actually means in a future video. This is just a basic overview. But just keep that in mind that static linking kind of allows more of that optimization to happen because the compiler and the linker kind of just, they can see more of the picture. Specifically, the linker can see more of the picture. Whereas dynamic linking, as I mentioned, happens at runtime. What that means is that when you actually launch your executable, that is when your dynamic link library gets loaded. So it's not actually part of the executable. When you launch a normal executable, it gets loaded into memory. However, if you have a dynamic link library, what that means is is that you actually link another library, an external binary file, dynamically at runtime. So you run your application, and then you load an additional file into memory. Now, the way that executables work, they can actually require certain libraries to be present, certain dynamic libraries, certain external files to be present before they actually let you run the application. That's why on Windows, for example, you might sometimes see, when you launch an application, you might sometimes see an error message pop up being like, blah, 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 .dll is required or is not found, so we can't start the program. And that's one form of dynamic linking. That's kind of, I like to almost call that kind of 50-50 because the executable is aware of the dynamic link library, and it actually lists it as a requirement, but it is still a separate file, a separate module that is loaded at runtime. You can also load dynamic link libraries completely, dynamically. So the executable can have nothing to do with it at all. You can launch your executable, your application, it won't even ask you to include a certain dynamic library, but then inside your executable, you can actually write code which looks for and maybe loads certain dynamic libraries at runtime, and then obtains function pointers or whatever you need to the stuff that's inside that dynamic library, and then uses that dynamic library. So with dynamic libraries, just keep that in mind. There's kind of the static dynamic version, which is basically, my application actually requires that this dynamic link library be present, and I'm already aware of what functions are in it and what I can use. But then there's also I want to arbitrarily load this dynamic library. I don't even know what's in it, but I want to pull out some stuff, or I want to do many things with it. And there are very good uses for both of them. We're actually going to focus on the former one for today, which is I know my application requires this library, but I'm going to link it dynamically instead of statically. So let's just jump into an example and look at what that looks like for GLFW, because GLFW actually lets us link either statically or dynamically. So in that static linking video, we basically just linked our GLFW statically. We included the header file and we called GLFW init. If I run the program, you'll see that it compiles successfully and it prints 1 as our result here. Now, not everything is going to change if you link dynamically. This include, for example, remains identical. I mean, the header file supports both static and dynamic linking. There are actually differences that need to occur with your declarations for things like functions if you want to link statically versus dynamically, and we'll explore that in a minute. But GLFW, like most libraries, actually kind of supports both static and dynamic linking with that same header file, as we'll see in a minute. So this doesn't change, and if I right click on my project and go to properties, you'll see that under C++ general, I have that include path. Again, if you're not 100% sure about how to set all of this up, definitely watch my last video on static linking. Even if you're only ever interested in dynamic linking, you still need to know what static linking is, because a lot of the time you'll actually probably want to link statically if you can instead of dynamically. So check that out if you're not sure. This doesn't change, and then if we go into linker input, we see that we have glfw3.lib. So if I open up my folder with glfw, and I'll just right click here, hit open folder in File Explorer, and then over here in my File Explorer, I'm just going to go back here into dependencies, glfw, and lib. So you can see here that I've got 3 files, glfw3.lib, which is clearly the one that we're actually currently linking, the static library. Let's go ahead and get rid of this one and replace it with the dynamic version. If we go back over here, you can see clearly that we have 2 kind of DLL files. Well, one of them is actually called glw3dll.lib. That one is just basically a series of pointers into kind of this DLL file, so that we don't have to actually retrieve the locations of everything at runtime. It's very important that these two are compiled at the same time, because if you try and kind of use a different static library to link with a DLL at runtime, you're probably going to get functions mismatching and wrong kind of memory addresses for function pointers, and just it's not going to work out, basically is what I'm saying. So this of course is distributed by GLFW, so they were compiled at the same time, and they are related directly to each other. You can't separate these two. So back over here, I'm going to type in glfw3dll.lib, and that's all we have to do from this side. Now if I hit OK, and I try and build this, it's going to work successfully, right? So you can see that it's generated my executable file. If I just move this over here, no one really cares about the error list anyway. Output is where it's at. I've moved this over here, you can see that hello-world.exe has successfully been generated. Let's try and launch our application now. Alright, and you can see that we get this error message that I talked about earlier. The code execution cannot proceed because glw3.dll was not found. This is where we actually have to show our program. This is glw3.dll, right? I've got it over here, please load it. And the way that we do that, in a simple case, is just basically placing that DLL file in the same location as our executable. So if I go over here, I can copy this DLL file, go back over here into dependencies, hello world, debug, and you can see this is the path with my executable. If I paste this in here, and I go back to either Visual Studio, I could have run it from there as well, and I try and run my program, you can see that it works successfully, and we actually get one over here. Alright, beautiful. If I go back over here to my actual Windows Explorer, I can also double click on Hello World, and you can see that it runs just fine in here without Visual Studio, without any kind of debuggers attached as well. So that's all there is to it. We link against the static library, and then we actually make sure that we have the DLL in an accessible place. You can, throughout your application, actually set paths to certain libraries, like search locations, but the root folder of your executable, so the folder that actually contains your application, is just automatically kind of a search path. So if you put it into the same folder, if you put your DLL file into the same folder as your executable, you'll be fine. Okay, so one more thing that I wanted to mention is if we take a look at this actual header file, we can kind of start to see the differences between what happens during static and dynamic linking. Specifically, if we look at pretty much any function over here, you'll see that it defines glfw API before the return type and then the actual function name. So if I go to the definition of that, and there's a few definitions, I'll just click on the first one, you can see we have this whole thing here. We've got this case for if we're on Windows and we're trying to build the DLL file, then it has to actually export the DLL functions. This is actually really important. If you build it without this, it's not going to work. Then there's also Win32 and just glfw DLL, which means we're calling glfw as a Win32 DLL, which does declspec DLL import. And then finally, there's also the building the static library, and then calling glfw as a static library, which just defines glfw API as nothing. So that's actually what's being defined right now. Now, here's an interesting question. We are still defining glfw API as nothing, even though we're using it as an actual DLL. So shouldn't glfw DLL be defined? If we go back to main, if I go to properties over here, and I go into my C++ preprocessor, and then I add that preprocessor definition, glfw DLL, let's try and compile the code one more time. Okay, seems pretty legit. Here it is, let's hit F5, and it runs, and it looks like it runs in exactly the same way. So what's going on here? Why did I not have to define declspec DLL import? Why did I have to just, even nothing works, and why is that? And that is a question for you guys. You've been asking me for a while to give you kind of challenges and things to do for homework or whatever. Here's a great example. Why is this happening? Why do I not have to actually declspec DLL import to be able to link to these functions in my DLL file successfully? Leave a comment below. Whoever wins this will just get pinned as the comment. I think that's a pretty decent prize, am I right? But yeah, just leave a comment below and we'll see who can figure it out. But anyway, thanks for watching. I hope you guys enjoyed this video. If you did, you can hit that like button. Any more questions about dynamic linking versus static linking, all that stuff, leave a comment below, as well as hop on my Discord, which is thetrainer.com/discord. There's a bunch of people there talking about pretty much everything to do with C++ and OpenGL and graphics and programming and just everything. It's a really good time. If you really like this video and you want to help support the series that I do here on YouTube, then you can go to patreon.com/thetrainer. You get some pretty cool rewards like getting videos early and lots of other fun stuff. So definitely check it out, and I'll see you guys next time. Goodbye. Hey, what's up guys? My name is Echeno. Welcome back to my C++ series. Today we're going to be talking all about how you can set up multiple projects in Visual Studio and how you can create a library that you can use in all of your projects. So this is something that's really important if you're working on anything kind of sizable. Not only does it help
multiple return values. So watch that. Okay, I'm actually making this up right. Multiple return values just
Hey, what's up, guys? My name is
can write a struct. Use a tuple.
Hey, what's up, guys? My name is Eternal, and welcome back to my series to actually define right. What happens is this specific variable. So what we can write std, which is how to create methods, and these are a normal kind of class as far as type that you want to surface. Once we actually get into kind of the game engine series as well, we'll start to see real examples of where we. So I'll just write type name t and then int n, right? So now I'm going to replace this int with t, and suddenly what I've got is an array of type t, which is specified at compile time by the template, that is of size n, which is also specified by compile time. So now over here, when I actually call this array, I have to specify int as an example and 5 for my size. And I can obviously change this to be anything I want, like std string and 50 or whatever, and you can see that what I've created is kind of a class that gets automatically created every time I actually use this array. So that's pretty cool. And what we've actually created here is very similar to how the standard array class actually works in the standard template library that's in C++, right? It just has two template arguments, type and size, and it creates an array very similar to the way we've actually done it here. Now this is a sort of meta programming in C++, because you can see, instead of actually programming what our code does at runtime, we're kind of programming what the compiler will actually do during compile time. And this is extremely powerful. Now what we're doing here, I think this is a pretty good kind of gentle introduction. We've even kind of gone as far as to create multiple template arguments and use integers instead of just kind of type names. But this is just scratching the surface. I mean, this can get really crazy really quickly. And because of that, hey, what's up, guys? My name is Eternal, and welcome back to my C++ series. So today we're going to be talking all about function pointers in C++, and specifically we're going to be talking about the kind of raw style function pointers that really come from C. So don't think that I'm kind of being misleading or anything like that. We are going to get into more the C++ way to do function pointers in a later video, along with things like lambdas, which I'll start off real simple here. Okay, so hello. Now let's assign integers autotype and imagine that literally when you and they're stored somewhere in our binary when we actually compile our code. In the future, we might actually take a deep dive into the binary file and see our actual CPU instructions and how all that works. But for now, just imagine that literally when you compile your code, every single function gets compiled into CPU instructions, and they are somewhere in our binary, in our executable file, right? So what we're doing over here with this ampersand is we're saying, hey, in this executable file, let's find this hello world function, and let's get the memory address of those CPU instructions. That's basically what this is, right? So what we're doing is we're retrieving the location. We actually managed to assign our function to a variable. Now, this is auto, but what type is this actually? Well, if we hover our mouse over this, look at what we get. We get void, and then like an asterisk, and then function, and some parentheses. Looks a bit weird. So let's actually write out that type. So we get void, then we need to give it some kind of name in our case because we are creating a variable. So before we called it function, let's call it function again. So in parentheses, I'm putting an asterisk followed by the name of my variable, and then any parameters that my function might take. So if it took an integer, I would put in int like that. If it took a string, I would put in string. Now we're not taking anything, as you can see. This is just no parameters here. So I can just kind of end it like that. This is the actual type. Now this does look weird because this is ultimately the type, kind of, right? It's just that we need to give it a name like any other variable, and function just happens to be the name. This can be cherno, this can be anything you want. It's just a name. And then what we can kind of do here is just assign cherno to, say, hello world or something like that. And you can see that it works like any other variable. And you can, of course, do that here as well. If I just write hello world, that also works like that. Okay, it does look very confusing. That's going to be step one. Like, I've called it cherno, I'll call cherno over here, like as if it was a function. If I hit F5, of course it still works. This does look confusing, I totally agree, which is why what people tend to do with function pointers like this is either use auto, or my kind of preferred way is actually to type def it or using it. So we're basically creating an alias for it. So what I mean by that is instead of this kind of weird code, what we can actually do is say type def, then this actual type here, and we can call it like our, I don't know,
using is
hello
better,
world
bro.
function or something like that, right? And of course, this hello world function name goes into here because that's our actual name. So it's basically the type, but we put a type def at the front. What that now means is that if I want to actually use this, I can just type in hello world function, then a variable name like function equals hello world, and then of course I can just call function like that. Okay, let's make this a little bit more exciting. I'm going to add a parameter here. It's going to be an integer. It's going to be called a, and then at the end of hello world, I'm actually going to print value and then a, just like that. Whoops, let's put this on the right side. All right, so now this hello world function, of course, we get an error here. We can't assign it because hello world is a function that takes in an integer. So what I'm going to do is change my function definition here to actually include an integer as a parameter. And now you can see this works. And when we call this function, which we're doing over here, we now need to specify an integer. So I'm going to type in 8 and then hit F5 to run my code. And you can see now I can do all of this and perform some kind of action. So of course, a for each integers called values, these values. And so what I'm going to do here is, inside for each, I'm actually going to write one more parameter here that actually is this function. So it's going to be void. The name I'm going to call is func, and then of course it takes one parameter, which is an int, and the values. That's what's happening over here, and you can see what that looks like. So if I hit F5, you can see what I get here. I get all these integers that I've got, 1, 5, 4, 2, and 3, as I defined with my list here, and I'm going to kind of do this. It's not declared as a normal function like with curly brackets, we basically tell it what we want it to do. So as if it was any other function. So we'll say print value, and then the actual value that we have. std function, which is standard function and standard bind and all that stuff. So there's a lot more to actually discuss to do. Hey, what's up, guys? My name is into here. All right, cool. So first of all, we start off a lambda with these square brackets. Let me make some room. We start off this lambda with the square brackets. What is that? Now, I will point out, first of all, that you don't really have to take my word for it or this video for it, because sometimes or this lambda is actually intended to modify and do whatever we want. And to fix that, you basically just add the word mutable here. It's a bit weird, but hey, stuff like that you probably wouldn't even realize exists if you don't look at things like the reference and see something into a normal function. But you can see here that we're copying the a variable, but if we try and assign a to something references video, and the pointers video is also related to that, all that stuff. If we go back to C++ reference, you can also see that we have the next step, which is the parameters, right? So those are the parameters that our function takes in. We have an optional specifier, such as mutable, which allows the body to modify parameters captured by copy. That's another thing that's kind of useful. You can see here that we're copying the a variable, but if we try and assign a to something like that, it's not going to let us, which is a bit weird because we're just passing it by value. And of course, if we were passing something into a normal function by value, of course we can reassign it into whatever we want. And to fix that, you basically just add the word mutable here. It's a bit weird, but hey, stuff like that you probably wouldn't even realize exists if you don't look at things like the reference and see what's possible, because you can see that over here we have our kind of parameters and whatever, which is one of them is that mutable optional kind of sequence of specifiers. Const expression is another one as well. Anyway, that's essentially how lambdas work. It's pretty simple. I don't want to order iterator equals std find f, and then we'll print out. We'll dereference that iterator and print it out. We should get the value 5 printing. Why? Because we've specified that we want a value greater than 3 using a lambda, and 5 happens to be the first number that is greater than 3 inside this list of values that we have. So if I just kind of put a breakpoint somewhere here and run my code, you'll see that we get the value 5 printing as we expected. And we've managed to do that fairly easily by just specifying a nice little quick function that we want this code to call. So what this is going to do is loop through our list, kind of like what I've got here in for each, and it's as if we just added a little if value greater than 5, then return kind of that value. That's basically what this is doing for us, but we're able to specify this if statement condition, this boolean, by just using a lambda really quickly like that. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. That's pretty much all there is to lambdas. Thank you, huge thank you as always to all of my Patreon supporters. You can head on over to patreon.com/.
All right. So let's go back to this. After this, I'll probably start programming. Until streaming SIMD extensions, until SSD2. Set of processor instructions that can greatly increase performance with the same operations to be applied on the data object. Firstly, for Intel extension. That's fans. Okay. Align us specify. To control the alignment of a type, use the align us specifier. Correct align us for food. Align as. I'm so cooked. Car A, car B, so it'll probably be car 2 bytes. And a struct bar which has an align as 2, car B, car A, and align as 8, car B, int B. Okay. And got a align as 8, int A, and align as 256. Standard byte. Standard byte is good. Alignment equals 4. Okay, that makes sense. Yeah, I agree with that. We feel like car. This will be Yeah, you have the int, the car, then the foot. Then you have the double that takes 8. You have the 7 specifying the alignment of not type is done using the align as specifier. This can take either an expression, an integral constant expression that provided by type ID or a parameter path. The align as specifier can be applied to the declaration of a class data member that does not represent a bit field, or to the declaration of a class, union, or enumeration. The type or object on which align as specification is applied by the alignment requirement. There are several restrictions. The only valid alignments are the powers of 2. Here the values are. It doesn't necessarily have to produce an error as a. An alignment of 0 is always ignored. The largest align as on a declaration is smaller than that without any. In the following example, the align as specifier has been applied to a class declaration. The natural alignment would have been 1, but the align as would become. Then instead of car A, car B, car A, car B, pad 2. The align as specifier can be applied both to the class declaration and the member data declaration. In this case, the strictest, that is largest value, wins. Following example, member A has a natural size of 1, and member B has a natural size of 4 because the strictest line would be 8. 4 was ignored because it's weaker than the 8. It'll be car A, then 7 bytes pad, and B for rest pad, yeah. You can also apply it to variables. Variable A, which is an integer, is required to be put in memory at a multiple of 8. Next variable, 4, is memory at a multiple of 256. As a result, you can power or introduce up to 244 bytes of padding between the two variables, depending on where the variable is. Looking at the addresses, we can see that the address of A is indeed a multiple of 8. The address of B is a multiple of 256. Through the alignment of a type, we use the align of up. Like size of, this operator can only be applied to types, not to variables, or class data members. Types can be applied to complete types, array types, or reference types. For arrays, the value that's returned is 0, the element type. For references, the value that's returned is the alignment of the reference type. The reference type. Line of car, I think it's gonna be, so I'm gonna try to not look at the answers. Line of int 4, line of int pointer 4, line of int 4, line of foo. What is foo? Yeah, I accidentally looked at 8 before. I was trying to look at the 1 for this. This, yeah, I agree, it's 8. Yeah. Optimize cache. Okay, how important in some categories of grief is trading application. First, the lineup. Using scoped enumerations. How long is it? Alright, so I think I'm gonna go back and debug. Here. Massive refactor. I think a solid way to debug this is using tests. I want to write tests a bit after the interface. So go into build, or what's next develop? CD into builds. Crash cmake dot dot. Build that. Sorry, cmake. Let's just build that. Let's just build. Let's just build that. Compile, no warning. And but if we run it, /source request such examples post direct compiling, lots of undefined behavior here, and yeah, we get some weird behavior. That. What happens if we do -j3? 3 jobs or something. So what if we just do dash version? Okay, I just get the. Does it bug if we do nothing? That's just. What if we do the entire directory? It doesn't actually. Big fault. Definitely some. And it's not erroring it. So how do you panic? Standard exit. Okay, so standards here. So put standard. Standard. Copy this here. West. Empty. I think this should be requests. This should track. Have a request reference rack. Okay, so that's already one improvement. See what that does. Getting a little better. Noticing that. Okay, that actually fixed something. That's hilarious. Let me go to the bathroom right quick. Alright. So you can see we still have a not printing any errors problem. We have a printing problem, concurrency problem. But it looks like the futures are actually working, which is nice. We're not actually using the threads before. We should probably make this. So if we use the counting semaphore, probably go here and do set thread sem dot acquire. Correct our thread sem. Direct thread sem. Calling the destroy. Give me a reference. So I think if it's just I don't think the type of this. Need to return. So the problem is you want to set this and then release the semaphore. Yeah, so auto run output to there and then this should fix some or it should minimize the object. We go here. Thread sem acquire. So we should probably construct them in here. Because we're already in placing back here. So let's actually construct them. If we do the file name in input file names.value. Here. Yeah, I don't want to copy it, it's a problem. So it is just string. You have all these file names. So yeah, let's actually just do this. Let's auto reference file name. Make a new request. Jesus. File name. Then we don't need that. You don't even need this list. Because they just exist. That's kind of dope. Okay, I think that's the best. You know what I'm saying. I think that should also be there. I'm gonna direct the future. Run the future. Clean up curl. Let's make this. Run that. Compiling, running. I think if you just do the whole dir with dash r. Compiling, running, compiling, running, compiling. Running. File. So implies we're getting some errors at some point. But never really printing. Let's see why that would be. In the request. Create a parser for parser. So when you get these errors, we are returning errors. So these futures return the so what is auto? That's that. Auto request. So if request is, let's bring a type in here. The vector of errors. So just a vector of errors. So that implies that we print. That's not a value. And it's not a vector. I should probably reserve. I reserve that. Let me copying that. Go. Errors. That looks pretty nice. In the constructor here. Also do and errors. Talk about errors. We don't actually have our own. Just return Oh, we return a vector. We don't even have our own array. Okay. But we make it on the stack. They're doing all these just for the inheritance. Yeah, I don't necessarily think that's good. I don't necessarily think that's necessary. Like, why can't we just return parse error? No viable conversion vector. Parse error to a vector with a unique. We need to move the unique pointer. You can't do that. Okay. Hmm. Do the errors exist? Here. They're a vector. Vector pressure. Standard expected is on the stack. That's freaking impossible. Hmm. So yeah, that is a bit interesting. But that's kind of out of the scope. Just trying to. We return the errors, but we never even. If if you did get empty. For each future and future. Or auto reference pointer, yeah. Error. And then error. Error. Try this. In 8. Error. From section head. Those look good. Hmm. So I think we need to bring back the lock. Also getting some curl error. Here's the file. Line number. So the line number's not working. That's pretty. That looks nice. That looks really nice. It is hard to read, but this curl error is very hard to read. So let's just simplify and go to post.rack. Filing, running. So running should say what it's running. Even the jobs will want. Curl error, pressure. Where do we see curl error? Two places. So if we, where do we throw a curl error? Parser. What is there? Go request execute. That's where it prints a run. Not curl, okay. Gotta rest. 43. Add function. Okay. Curl underscore. Acting like it's not underscore. E3. No internal thread synchronous. Handle. Up, no signal needs to be easy. Yeah, the curl isn't even, it's not even like straight up incorrect. So this wasn't right. So the curl. Okay, so if you're a man, curl couple. So I think in the constructor, what's the constructor of curl? I think curl. Dixon. What? Yeah, we did the constructor. Clowning. Hmm. Yeah, my bad. Maybe this here. Ease. Definitely here. Am I cooked? Why is this not working? Oh yeah. So in here. Curl. Just curl. Oh. Better references. Yeah, that's interesting. Did each of them have their own curl? Like, yeah, I don't know. No curl error. So the assertion errors are fine. Parser. So by default, you want to see the response. That fixed that. Post.rack. Hmm. Is there a deadlock? I think there's a deadlock somewhere. Maybe that's J1. Hmm. Yeah, it seems like there's a deadlock somewhere, dude. Um, that's alarming. Remember this. Okay. So, make that a bit more explicit. We're gonna go into code request. Rename this code. There's a deadlock somewhere. So I think the default behavior should be a key. Doesn't. These ops. Kind of setting these ops. Right function. This is gonna be the right function. Go there. Body. Where's the third function? This should. Turn something that's on this. It's gonna copy it. Copy. I want to copy the map. Copy construct. Hmm. Named return value. But I actually want unique project. Mm-hmm. Yeah, wherever we use. Actually, just not worry about copies. Yeah, let's just not worry about the copies for it. Look, I want to have some tests. I'll come back and do all the copies and make them more performant after the test. Okay, so we got the lock on post. Everything else, and now we still have the. There's a dialog here. And this. And the printing messed up. Yeah. That's not good. I'm also just trying to consider, how do I want this to... I think the curl stuff is all that's it. Also, I like to look at C++ format, format versus... Yeah. Hmm. Hmm. Yeah. Hmm. Okay. I'm gonna get something to eat. Be right back. Got a little pizza. Oh, let's move through some more China.
Hey, what's up guys, my name is Achona and welcome back to my C++ series. So in the last video, I explained why I don't like using namespace std. If you guys haven't checked that video out, definitely do so. But I haven't actually talked about what namespaces are in this C++ series, and because in that video I specifically wanted to talk about the standard namespace and why I don't like using namespace std. But today we're going to be talking about what namespaces are in C++, why they're useful, when I wouldn't use them, why they exist, and all the different things that we can do with them. So if we jump right into this is the code that we had written in that previous video where we talked about why I don't like using namespace everywhere and all that kind of stuff. Let's talk a little bit about what we actually see on the screen here and how we can further extend our usage of namespaces and why namespaces are actually used and necessary. So over here, we essentially have this issue where we have two print functions. Now they do have different signatures. One of these takes in a string, one of these takes in a const char. But if we kind of revert to maybe both of them taking in a const char, so if I change this string one to actually take in a const char pointer like so, we kind of may have an issue if we weren't using namespaces, because these functions are identical. If I just kind of comment out this namespace apple line of code here and the orange one as well, suddenly we have a little bit of an issue. If I try and, I'll fix up this error as well, if I try and just compile this by hitting Control F7, you can see over here that I get an error because it's telling me that this print function that takes in a const char pointer already has a body, because I have two symbols with the same name and they're identical symbols. Now when I say symbols, I'm talking about things like classes, functions, variables, constants, that kind of thing, right? So we have in this case two functions called print, which take in const char pointer and return void. They have the same signature. So these two symbols are identical. We can't have two identical symbols. That's a linking error and potentially a compilation error in there if they're actually in the same file. So how do we fix that? What if we do want to have two print functions? Or what if we use another library that has already defined a print function, but we want to have our own print function? Now, back in the days of C, and in fact that still is a thing, C doesn't have namespaces, which is why, if you would have noticed in the OpenGL series as an example, we're using a library called glfw, which is an OpenGL kind of windowing and context library and input and all that kind of stuff, right? But the point is, glfw is a C library. It's compatible with both C and C++. Because it's a C library, they can't use namespaces, which is why, if you notice in that series, all of the code that we write that has something to do with glfw begins with, like, literally every function starts with glfw and then like the function name. For example, glfw init or glfw create window. All of that stuff has glfw literally prepended to the front of it. With OpenGL, it's kind of the same thing as well. We have GL and then the symbol name. So like GL begin, GL end, GL gen vertex buffers, that kind of thing, right? We have the actual name of the library or some kind of ID embedded into the function name. So in our code, that would be the equivalent of if I had literally written something like apple print, right? And orange print. And then now you can see that, oh, okay, these two functions are different because this is like the apple print version, this is the orange print version. And that's actually what C libraries tend to do, because they can't just, you know, I can't make a function just called init, because init is such a common name. What if, you know, if every library was to just name their functions init, then you could never use those libraries together without having to modify the source code. So what they do usually is just kind of prepend the name of the library to it. So glfw init. And that works because, well, it's a fairly unique name, right? glfw init. Okay, cool. That's specific to that glfw library. Now in C++, instead of us having to do all this, we have namespaces to solve that issue. The primary purpose of namespaces is to avoid naming conflicts. That's why they exist, to avoid naming conflicts, okay? That's it, sort of. Just if you're getting confused by why namespaces exist or why they're being used, it's because of naming. We want to be able to call symbols the same name in different contexts. So if we go back here into Apple Print, instead of having this, what we can do is enclose this symbol in a namespace. In this case, what we write is namespace, the name of the namespace, and then, just as if it was any kind of function, we surround it with curly braces, which everything in between these curly brackets is included in that Apple namespace. Now, personally, I like to write my curly bracket on the same line as the actual namespace declaration. I don't like doing this. The reason that happens is because when we have multiple nested namespaces, it gets a little bit messy. So what I like to do is, if we had Apple and then maybe like functions or something, you know, I have this here, and also with the end braces, instead of kind of writing it this way, which is what Visual Studio will try and auto format it to, I like to just have it on the same line. That way my actual functions are one level indented and not like 2 or 3 or 4, or depending on how many namespaces we actually have nested. So that's just my personal preference. You don't have to follow that, but that's why I kind of put all this stuff on the same line. So that being said, we now have an Apple print function. If I go over here into Orange and get rid of these comments as well, we have this orange print function. I can rename it to just print. So we're able to have two functions with exactly the same signature in this file. And when it comes time to call it, what we do is we need to specify which one we need to call. So print is now inside either the Apple or the Orange namespace. We have two of them. So if we want to use the one from Apple, we just type apple : and then print. This : is essentially like a namespace operator. So what you do is every kind of namespace that as you drill down into a namespace, you just put a : and that is what, I guess, enters into that namespace, or allows you to call things from that namespace. The same thing applies to static functions, I guess, or symbols in classes, and like methods in classes and all that stuff. A class is kind of like a namespace. It is a namespace of its own, which is why if we're accessing like an inner class inside another class, or like an enum, or, you know, like I gave the example of like static functions or even non-static functions in some cases, we use : So that's what the : kind of means. So this double colon is used to get the print function from the Apple. And if we were to run this, we would just get hello printing normally. If I want to call the orange one, obviously I type in orange. Now that whole using namespace thing that we talked about in the last episode was just a way to not have to write this kind of Apple or orange kind of prefix. So instead of having to do this, what we can say is that actually we're using namespace Apple, which means that basically import everything from namespace Apple as if I had never specified it as a namespace. So in this case, print will be used from Apple. If I want, I can change it to orange. I can also say, if we have multiple things in here, like we have print and maybe print, I don't know, print again or something. If I have multiple functions, maybe I don't want to use print again from orange. I just want to, sorry, that's an apple. So let's go to using namespace Apple. Maybe I don't want print again. When I put this using namespace, I don't want to use print again. I still want to specify maybe which print again I just want print to be imported. So to do that, we can just write using Apple and then the function name print. Okay, that means that we're going to take this from the Apple namespace specifically, but for this, we'd still have to specify that namespace like that. You can also create aliases for namespaces by just typing in namespace, you know, A equals Apple or something like that. That means I can type in A print like that instead of having to spell out Apple. That's very useful for when you have nested namespaces. So we can also nest namespaces, as you probably saw earlier. So we can have Apple and maybe we enclose all of our functions inside of this functions namespace for some reason. Don't ask me why, just an example. So we have namespace Apple, we have namespace functions, and then instead of us having to write, you know, Apple functions like that, or, you know, something like using namespace Apple functions like this, we could also, by the way, for this example, you can also split this up. So you can be like using namespace Apple and using namespace functions, which would allow us to not have to specify any namespace for print at all. So instead of us having to do this, or in the earlier example, that, we can also just say namespace A equals Apple functions, which means that I can just type in A print as if it was one namespace and I would get that result over there. Okay, so that's a pretty basic example of how namespaces work. I'm not sure if there's really anything else that I need to talk about. Obviously, things like this are confined to the actual scope. So in other words, Hey, what's up guys? My name is Eterno. Welcome back to my C++ series. Today, we're going to be talking all about threads and in general how we can parallelize, that's a hard word, how we can make stuff happen in parallel, because most of the computers or processors or devices that we're programming for nowadays have more than one logical thread of processing that they can actually do. So far, all the code that we've been writing in the C++ series and the OpenGL series as well, if you guys are watching that, has been on a single thread, which means that when we actually write code for those episodes and for those series, we're literally just making the computer do things one kind of line of code at a time, or one instruction at a time, which is fine. A lot of the things that we've written have obviously not been particularly fast, or that they haven't needed to be really like well optimized or really quick, because we haven't really written any heavy code, any code that will actually take the device a long time to compute. It's been really simple stuff. But as we get into more complex programs, it's very beneficial for us to actually move off certain work to different threads of execution, not just for the sake of kind of performance, but also for the sake of what we can actually do with that. For example, we've used stdcin.get to request input from the user into the console. However, we can't do anything while we're waiting for input, can we? We're literally just waiting to receive input, and that's kind of like a while true loop that's just going on infinitely. And until we press enter, that's it, like our thread is blocked. But what if we could maybe do something else, like print something to the console, or just log something, or write a file, or whatever, while we're actually waiting for user input? We still want other things to happen. That's one example that's probably really simple to understand. But anyway, we're just going to dive right into the code and see what we can actually do. Alright, so the first thing I'm going to do is just show you kind of how threads work and what we can do with them. So I'm going to include this thread header that we have here, which includes the threading support basically into this file so that we can use the thread class and everything. I'm going to type in std thread. I'm going to call it something, so I'll call this a worker because it's going to be like our worker thread. And then what I need to do is pass in a function and optionally any kind of arguments that it may need. So let's make a function called doWork. This is going to be the function that actually performs what we want to happen on another thread of execution. So I'm going to pass it into here by just typing in doWork. If you guys haven't seen my function pointers video, definitely check that out because this is how this works. It takes in a function pointer. That's why we just pass in do work without parentheses or anything like that. Video link will be up there. And as soon as we write this actual code, it's going to immediately kick off that thread and it's going to do whatever is in here, and it's going to keep running until we wait for it to exit. So the way that we can actually wait for something to finish or wait for a thread to complete its work is by typing in worker.join. So this is our thread object, of course, and then this join function is essentially going to just wait for this thread to be joined. Now, thread joining is another kind of potentially complex topic that might be worth discussing in more detail, but basically in C# and kind of more modern programming, it's just called wait, or wait for exit, or just, yeah, wait is probably reasonable. Basically, all that this does is it just says, hey, can you wait on the current thread for this thread to finish its work? So block the current thread until this other thread has completed. So because this stuff is running in parallel, we have our main thread, which starts off a worker thread, which does its work. And then eventually what we're doing by writing this join kind of call here is we're saying on the main thread, wait for that worker thread to finish all of its execution before we continue on with whatever our main thread has. So what that means is that this cn.get line of code will not run, because it's the next line of code after this. It will not run until everything that is in this function has finished. And we'll see this in practice in just a second as well. So as an example, what I'm going to do now is let's just dive right into it, and I'll demonstrate that example that I made with cn.get. If we just write a normal program, maybe we want work to be done that prints something to the console. We'll say it prints working to the console, just like that. And it's going to kind of keep running forever. We essentially want it to just run forever. So I'll put this into here. If we were to want to write something like this, that performs any kind of work that happens until we tell it to stop by maybe hitting enter, how would we go about doing this? Well, we know that what we could do is we could say, well, okay, cn.get, so maybe we want this while loop to continue until cn.get actually returns something, because cn.get will just wait for us to basically press enter. So we want to write a program that waits until we press enter, but the line of code that waits until we press enter blocks execution because it's waiting for us to press enter. So it can't actually print working continuously because it's waiting for us to press enter. So on one thread, this doesn't really work. We need to be able to do two things at the same time. We want to be able to wait for the user to press enter and repeatedly check to see has the user pressed enter, but then we also want to log working to the console. So let's look at one way that we might solve this. So what I'm going to do is write a static boolean here called sWorking, and or we'll call it sFinished, and I'll set it equal to false because we haven't finished yet. And then this while loop will run until finished has been set to true. So while not finished, keep printing out working. And then what I'm going to do over here is stdcn.get, which blocks this thread until we press enter. And after we press enter, I'm going to set finish to true. And then I'm going to just wait for this worker thread to join. So what's happening here, if we look at this kind of concurrently and how it's actually running, this is printing working as fast as it can to the console, and that's all it's doing. This thread is waiting for us to press the enter key, and when we do, it advances to line 19, which sets finish to true. The next time this checks the state of finished, it will see that, oh, it's been set to true, which means that I'm finished, so it's going to advance past this while loop, and that's the end of the function, thus that thread has finished. And this is going to make sure that we don't do cn.get until that thread has actually finished its execution. So if we just hit F5 and see what this actually does, you can see over here that it's repeatedly printing working, and when I press enter, that's it. It stops printing working, and if I press enter again, it's going to terminate our program because we have another cn.get over here which waits for that before it just closes our program. So maybe instead of printing working as fast as possible, we might want to say, well, actually, let's wait for a bit. The thing with multi-threading is that if you continually do things as fast as possible like this, it is going to kind of result in like 100% CPU usage for that thread, which isn't great. So what we can do is we can say, well, wait for a bit. And what I'm going to do here is just tell this current thread to sleep. So I'm going to write sleep for, and then 1s, which stands for 1 second. And in order to write code like that, I'm going to have to using namespace chrono literals. Okay, so basically I'm just saying after you print this working line of code, just sleep for a second before you go back up to this while loop and continue printing working until finished is set to true. So if I hit F5 now, we should get working printing to the console once every second. And there we go, you can see that it's ticking like that, working, and if I press enter, then that's it. It's done. And in fact, let's just maybe write something to just indicate that it's done. So after worker.join, I'll print finished. And let's see what that looks like. So there we go, working, enter, and you can see we finished, and that is the end of our execution. So that's a very basic example of how threads work, arguably fairly useless, but the point of this video is just to show you, first of all, how you can access threads in the C++ API. Of course, this ends up boiling down to platform-specific code, but you just need to include thread, and when you just make a thread object by typing in std thread and then you make a variable out of it and you pass in a function to the constructor, that immediately kicks off that thread, doing whatever work you've made it do, and that thread will continue until it's done. You can always use like that thread.join to actually wait for the current thread that's kicked off that second thread to actually finish its execution, in case you need to do some kind of cleanup or wait like this for the actual program to terminate after all the threads are done. That's as far as the API goes. There's really not a lot of things you can do. There's not a lot of things you need to do. The concept of threads is really, really simple, but it gets really complicated really quickly, like a lot of things do in C++. The std this thread thing as well can just make sure, there's also a this thread object that I used here. If I just grab my laptop again, we have this std this thread, which you can use to actually basically give commands to the current thread, because you can see that in this thread I don't have access to this thread object even though I'm actually on it. So what I could do, for example, is just print the thread ID that I'm on. So I might say something like std cout started thread ID equals, and then I'll print the actual thread ID by typing in std this thread get ID, and then I'll copy that line of code and also print it maybe after we finish over here. And these thread IDs should be different because they're running on different threads. So if I hit F5 to run my program, you can see we started thread ID 8348, and then if I hit enter, you can see it's a completely different ID because they're actually on different threads of execution. We've created another thread to print our working stuff to the console. So yeah, threads are really important. We're going to be talking a lot more about them in the future. They're really useful for speeding up your program. Hey, what's up guys? My name is Eterno. Welcome back to my C++ series. So today we're going to be talking all about timing. So how do we time how long it takes for us to complete a certain operation or
Alright, so let's do timing. And then okay, let's not do timing. Let's do scoped enumerations. And then back to alright. Enumeration is a basic type in C++. Okay, so yeah, I didn't know anything about scoped enumerations. Where do you scope enumeration? I'll declare them using enum class or enum struct. They're equivalent. Because scope enumerations are restricted namespaces, C++20 standard allows us to associate them with a using directive. You can do the following. Introduce a scoped enumeration identifier in the local scope of the using directive as follows. Using status unknown. Status equals unknown. Kind of like the explicitness of knowing it's a status, but you can introduce all the identifiers of a scoped enumeration in the local scope for the using directive as follows. So, struct foo has an enum. It's using the enum. And so foo status foo created. Okay. Use a using enum directive to introduce the enum identifiers in a switch statement to simplify your code. That's nice. I think that's a good idea. Converting a scoped enumeration to its underlying type is sometimes necessary, especially in the context of using old-style APIs that take integers as arguments. In C++23, you can convert to the underlying type of a scoped enumeration by using the std_to_underlying utility function. The old API needs an unsigned flag. Enum class user writes unsigned, you have none. Read is 1, write is 2, delete is 4. Std_to_underlying user writes read. That's good. I like that. Notable C++23. Unscoped enumerations have several issues that create problems for developers. They export their enumerations to the surrounding scope. Which reason they code unscoped enumeration. It has the following two drawbacks. It can lead to name clashes if two enumerations are in the same namespace. So yeah, it's not possible to use an enumeration. That is kind of annoying. Oh, what? Values of enumerators implicitly in intentional URL versions of managers. Or not. They're strongly type enumerators. Yeah, so definitely use the scoped. I didn't know that. I feel like that's. I thought that would be the default behavior. This is a C++ 20, C++ 11. Values of scoped enums no longer implicitly convert to int if to static cast it. However, the scoped enumerations have a drawback. They restrict namespaces. Do not export the identifiers in the outer scope, which can be inconvenient at times. You're writing a switch. TPP20, this can be simplified with the help of a using directive. Scoped enumeration. Code can be using enum status. Case unknown, case created. Yeah, that's good. Local scope. Status connected. TPP23. Type of utility function. Standard 2 underline utility header. You can work with APIs that don't use scoped enums. Consider the following function on API, which takes an integer argument. It's just flags. Read, delete, and conversely, a newer part of its system defines the following scoped enumeration for the user rights. User rights unsigned, you do them, and then not possible. Static cat must be used. Avoid the static cast. To underline. The other utility introduced in CPP23 is a type trait called isScopedEnum of T variable. The type traits header. This contains a member constant of value, which is equal to true if the template type parameter T scoped enumeration type or false otherwise. There's also a helper variable template isScopedEnum. The purpose of this type trait is to identify whether an enumeration is scoped or not, or to apply different behaviors depending on the type. Here's a simple. Enum A, enum class B. Let's see out. Is scoped enum A. So it'll just print out B. Oh, okay, yeah. Using override and final for virtual methods. So this is kind of relevant to my error thing. How long is this? 3 pages. All right, we're gonna read this. Unlike other similar programming languages, C++ does not have specific syntax for declaring interfaces. Interfaces are just classes with pure virtual methods. and also has some deficiencies related to how virtual methods in CPP. The virtual methods are introduced with the virtual keyword. However, the keyword virtual is optional during override class. Lead to confusion dealing with classes. You may need to navigate through the hierarchy up to the base to figure out whether a function is virtual or not. Conversely, sometimes it is useful to make sure that a virtual function or even a derived class can be overridden or derived further. Next recipe, we'll see how to use the CPP11 special identifiers override and final to declare virtual classes. So I'm not too comfortable with this, but let's ensure the declaration of virtual is both in base and derived class. Also ensuring that you increase readability following. Aim to use the virtual keyword when declaring virtual functions in derived classes that are supposed to override virtual functions from the base class. Always use the override special identifier after the declarated part of the virtual function declaration or definition. You have a class base, which has foobar and foobar functions, all virtual. It's even defining void base foobar. Of the derived class 1. Virtual override. Decorator is a part of the type of the function that includes it. Okay. Ensure that the functions cannot be overridden further or that classes cannot be derived anymore. Use the final identifier. After the declarator part of a virtual function declaration or definition, prevent further overrides in a derived class. Final virtual. After the name of the class, declaration to derived final. The override works is pretty simple. In a virtual function declaration or definition, it ensures that the function overrides a base class. Otherwise, it should be noted that both the override and final special identifier have them in the member function. They're not reserved keywords and can still be used elsewhere. Using the override special identifier helps the situation for virtual, not override another. As in the following example. That's a good point. Without the presence of, yeah, if you have the parameter, it's not the same type, but you're kind of thinking it is because actually there is this. Miniature using. So them use them in code. That's interesting, but we just gotta. So let's just implement what they said for the error shit. Where's the base error? It's just in a header. It is. I don't think this should exist anymore. I think this function. So when you put the virtual keyword in the class, virtual destructor for error is default. So it's not. This should really just be in padding. This is kind of bad design. Okay, so we need to make a logger. It really needs to be. All inline. Make a there should be the logger should be in effect a so this was horrible. Having format in the error is just freaking gross. So that's a class logger. Yeah, the logger, dude. So in the public scope, so director for a logger. So this should really be a singleton. Safe singleton for printing output and error. A logger constructor. Should take in a habit context, reference text. And just for convenience. How do you make a thread safe single? UG23. David. Dead. Instance. You have a static fun. So this is like the get. All one. Um. There's also some. How do you make it start with an app contact? Hmm. Hmm. Yeah, should I don't feel like a logger should be. I'm gonna acquire the lock. Yeah. When you start the program up, that's in verb. Back to the construct. There's that thing where we had the. So instead of actually taking an app context, have a public enum as um, verbosity. What was I just reading here? Scoped enumeration. Verbosity. Bug mode. No. Quiet. Bold. And verbose. Here I have velocity. By default. Okay. So you have a verbosity. Over the app context. We're gonna have velocity. Hmm. If x else if c. Redefinition of. Wow. Playing that the last buffer I was at. How's this not? Going with this. Const app context reference. Logger. Redefinition. From the logger. Would you be able to have? I feel like that's really all you have, and then if you go to printer, you have all these combined. Need a standard string reference. Oh man. Running. If you said compiling, right? It should only have. You could have. Oh. Oh, we're enabled. Where But I think we actually shouldn't have defaults because they must be crap. TPP. Or enable. Not see. Picture the. Yeah. Print line and left. Seven error. Rotate it. Error reference. Error. So you can print compiling. You're running. Error. You can also avoid. You can print the response. Response. I think that makes sense. That's really all the functions we should have. Filing, running, error, and response. Let me remove soon. So the thing is that we'll have one static logger. Yeah. But that's not the question because you're then you're gonna have to pass those logger up. It's also not a logger for the application. A logger. Might be better to call this printer. So this probably should end up being the printer. We can just do, go ahead and just get rid of the printer. And start that by probably comp time. Right line and left pad is pretty. Final error. We could just call this the curve printer HPP. Rename this. Name this. Name log. I have no idea how that's not. Parser colon parser. Yo, why is that not right? Name. Void error. Fixing errors. Yours is one. So the print function should. What is the parent constructor? Hmm. Bathroom man quick. 8. I forgot my shoes. All right, so what was I doing here? Um, yeah, this is horrible. Most of this should actually go into error. Interestingly. There's really no way to freaking unfill that. In an error. It does this generic shite. Never really used that. Is there this? This. Pushing severity. It's gonna look like this. I'm gonna say error. Title. Error has a title. Back here to error. Everything has file name. Constant. Constant. So this is not. Earth rate is. And logger error. Error was Why we're a friend, bro. There's error. Sec. So I was actually looking this up just a second ago. About this, the explicit private constant. Structure should on it. I don't think I'm gonna. For instance, earlier. Could have been final there. It is indeed an error. I need a file name. You're getting. And then here you do the error construct. I guess that's the end. What's unique to curl error is probably just the curl error. Actually move this here. Type and have for the types. I forget. Had some errors. Yeah. Curl. Curl. You want to have a right. Something you can do with the type is title. So instead of the enum, you can have the enum and then map all the enums to the types. Instead of title, I think a better word there is going to be brief. Second curler. With the brief. So you should really have the brief, but the brief comes from type. You know what I mean? There should really be a curler. Be a type. That will there. And you have the uninitialized girl. Okay. That's the only one. Kind of main. But the problem is when you want to construct it here. That is curious. I'm gonna construct it and then have the run. The best way to do it would be to have the printer. Then just not make it construct here. Start with the verbosity default. Or enable true. In main. You could just link in printer. But then you get away with verbosity. You don't even need other bullshit. You have verbose. And friend main. Yeah, verbose. Oh my god, that's so AIDS. Yeah, you will need a virtual method. We're gonna add that. Logger dot. It's only gonna be do that. Speed up contacts. Size. Okay. Should I change? Unique point. Tested. So this is brief. That can be a. The brief should be. That's crazy. Counts expression inline verse standard. Get brief. Counts expert inline doesn't even. Then what are the over? A foot. Okay. Hint. The hint. Hmm. Yeah, it can't do a reference to something. Not a reference. I think it should be not a reference. Go to error HPP. So detail. Huh? So you need the file name reference. Error constructor. File name. Just had that on my phone. Hmm. So you don't do it like that. Like this. I do override. Brief. That's expression. Sweet. Where brief first. Do this. Curvature. pitch, type, name. Like that. So you actually just want to use print. Huh? Did I actually misclick that? Acting it doesn't even. Dude, that's why I did this on. Yourself. Parser error is definitely in 5 errors. Gonna take it. So also the thing I was doing with parser error, standard variant. So it could be on the stack. Why is brief doing nothing? Yeah. Conflict sphere to map inner error type in title. Output. Uh, we're still gonna do with a hint. I think hint might literally only be a thing. Or sure. I'm gonna move that. I'm gonna move this here. Wanted parser error HPP. We had this variant thing going on. Effectively. I think this should just be part of brief. The hint. No, because the hint is not constant. Yeah, it's not part of brief. Part of print. Move this down, public. Gee. Of the construct. So the way that was working You have a video on standard variant. Oh. VP standard variant. It is like a here. And then here. This is kind of this is all cons. Cons experiment. Where is this? Yeah, so this is kind of crazy. Hmm. Right now. That is kind of wow. I kind of mess. Hmm. So instead of having a type, you do type. This gets away with the heat. That is kind of complicated. Let me look at GPT. See what the performance. Let's see if we can get an answer on that. You don't need it. Don't need it. Don't want him. There it is. Don't have the fun. Inputted constructors. Dang, that's freaking crazy. Doesn't have a this shouldn't be. Then going to pressure CPP. Give the file name. That I'm gonna get brief. Lambda. Taking in auto double reference. Wow. That's freaking insane, dude. That is easy. This is an account. Yeah, it's in the print function where we're gonna want in the printer. Hide that. You should really. Mean. It does actually. It does actively print it, so maybe we should use a string code. right here. Get macro. Get macro. That 9 on this pad is not defined. Oh, it's not defined for no op. That 9 on that pad with no op. Yeah, it is. There's certainly some errors. Let's see. Yes, there's error severity over for sure. That worked, dude. Passing around the heap allocated, it really should just pick them that. No key, just don't print compiling. Okay. Error severity. Error. What? File name. Reference. What does it say about using it? Put it in a. Put it in. Enter. Yeah. Hmm. Doesn't know anything about the. That is annoying. Running. It is easy to just removing. Remove it for now. You need. It has that ring there. That wasn't good. I can actually fix this by doing search and error type. Be a search and error. Also do a ss.spare. Now we're inlining this line. error severity usage. Oh, file area. I forgot. I'm gonna need the. Oops. I'm gonna need the 3 minutes. Everything. Earlier. Um, they type and this here. And that. It's just gonna be it. Here. Details. There. Here. Yeah, things. Throw error, the file error. Type your house. Bad. So, still using error severity. Oh yeah, I forgot about that. That was the last thing I forgot to do was file. Type that here. Nice. Get one error. The linking stage is reference to it. So I did make some new files. Just see. Printer, let's see. Let's go alpha. Airs at the top. Surgeon here. Burrow fire parser. You got assertions. Burrow request and fancy parser. I don't think that fixes. Okay, so now we apt context. This doesn't take. Yeah, I forgot I was in the middle of it. This has been a part of Go to main. This global printer thing doesn't work. Huh. Hmm. How do I want to construct a... I feel like it should just be a set of functions, but then how are you gonna know about the verbosity? That's Jupiter. Yeah, I'm not really sure how to design this. Dude, I forget how bright stuff can be. But it is a bit of a singleton. Hmm. Okay, that looks good. Okay. The C++ modules that great. I'll do it just for fun. Problem is I won't have all the same. Dang, lock guard is deprecated. Okay. I don't understand why it needs to be backwards compatible. Don't upgrade. I mean, alright, let's write a CPP module, bruh. Let's make this Mitch a module, bruh. At the very top, you do export. Uh, Problem is that it relies on the errors and Hmm. I think you just see. Why is it freaking bugging so? Dude. Uh, I don't think the module's the right use for this, Loki. Yeah, I don't think the module's the move. Or just been using format. So I probably do want to bring the verbosity back. Um, hmm. Well, no, because we can do the friend main with verbose quiet controller enable all these functions, and then just do here the printer reference printer. So in printer SIPP, for there, constructor, actually no constructor. Set up a constructor, you have a printer reference is a static printer. Printer instance. Error.get brief. That is. Error fert. Oh yeah, we didn't even use it properly. What am I doing, dude? So in main, you don't do this anymore. Do you even need app context? You could use app context, but you don't need that. Because you have the global printer. Printer.quiet. Printer dot. No color. On this inner printer HPP. Color enabled. Is there a way to like invert it? More linker problems. Enter error footer int. Hmm. It is right here. Enter.cpp. Go to definition. Hmm. I need to redo the CMake. Did I include print? I forgot the mutex. Error footer is right here. But I didn't mark it in line. Right. I did mark it. I don't want to see where that. Show an undefined reference. Avoid error footer. I'm really not seeing how that would link. First main.cpp be linking plus the link. First files. I'm not seeing it. Same with print line and left pad. Cursor. So this should be here. This should be here. Because there's that. I want to get brief. Rid of the air. All of them have this function, get brief. Fine. They didn't make it. Those are not defined for. It's kind of dumb to end. Does it require this? No. They're gonna have the same errors. Hmm. It does make a bit of sense. It's not forcibly returning a string. Okay, so I did do that. Basically, you just need a default. Throw request. Taking 2 millions. Go ahead and see if we resolve this one. Oh, it already printed. Undefined reference enter. Error footer. Gosh. Main. Printer. Ah! Printer, yeah. Printer. Try one more. It's virtual. I don't think it should technically have to be version. Yeah, I'm not sure how it's saying them. Oh, it's freaking. So the printer has it. Void print line and left pad. Talking about air footer. That's the problem. Has it out of line. Void printer. Allowing cons. Oh, these cons. So they should be. I should just. Oh, there. Make the mutex mutable. Make these calls. That is the best way. There we go. Now we just have the parser error. Type in for reference. Seems like a linker error. Undefined reference to parser error, parser malform section header const. So this is the parser error constructor. Okay. Parser error, parser error. The type name being All right. All right. Let me make a bev very quick. What GPT has to say about that? You need that? I didn't know that. No, you need. Okay, then you should be in the header. That makes sense, Wiki. Oh my god, this song is horrible. Dude, what is this? Holy. Oh, this might have been the worst song I've ever heard. Yeah, let's move that up. Makes sense. Yeah. They're doing a double reference. Yeah, that is kind of dumb. Yeah. So, constructor takes a file name and a T. Oh my god, the reason I was doing it is because of this. Parser shouldn't even have a file name. Did it? Yeah, it should. Should have a file name, but it should certainly be a reference. Oh my gosh, I'm so slow. It, it's not const. Oh my god, I'm cooked. Not that. What's the parser constructor? Yeah, well, that was very dumb. Files and IFs. Use an iterator. Probably be it. Const. Matching constructor. Right, back to this BS. Wait, did I write cons for no reason? Yeah, I wrote cons for no reason. What's the problem? Holy skill issue. You're gonna need to stood move it. No, you're not. That's cap. Just turn it for being. So in Archer Air E9 HPP. Okay. Definition. No matching function for call to variant. Hmm. Let's just try the pass by dot. Good with that. Good a Purser CPP. Good a Purser, sorry. It's closed initially. It's in. Good there. Hmm. You know if that's talking. I don't think it's even gotten to the. I think that's it. This can't be a thing, dude. I feel like that. Errors is a vector of cursor errors. This needs to be cursor error. Hmm. This is difficult, dude. I do use the global reference thing. For it, and if the type is could be that was that's clear in it. Yeah, because there's a pointer here. Parser 120. I think that's a two type set. Type info and error. Okay, so we fixed that. Easy. So now we're back to this type info and error BS. I'm gonna find a reference to type info. Back to error. Dude, do I really need to do a freaking undefined reference type info? Okay, I need that. I'm convinced I need that. I'm gonna do something. Only thing that's here is a string reference. Undefined reference. Hmm. Pure virtual has a 0. There we go. Oh my gosh, it builds. See what it looks like. Source, request, slash examples, post, rank. I forgot I disabled console output. Green. Okay. Ugh. Here's the pure virtual. That's what I needed. Gotta answer some other question right quick. Hmm. Sorry, I'm a bit distracted. Gotta do this right now. Right quick. Hmm. This was $31. Jesus. I've opened this so many times too. I hope it's not recharging every time. It'll send me the freaking. No offense. Alright, so let's get back to this. So we're getting the errors not with their headers though, so. See if we can get on top of here. The errors to. Not a dead bug. Oh no. Oof, that's not good. Okay. The weak code on error that is abstract. As a non-virtual. I think I need that back. Okay, so if we get here, to actually print the result. So I think we should actually do a standard selected. Either that or have a standard unique pointer to just a to a curl request. Response. Mm-hmm. So confused. Standard expected. Unique pointer corresponds or a vector of unique pointers. Errors, close unique. That was very complicated. Be a standard unexpected. Template. Matching function. Can you just imply doing this? What's wrong with that? Unexpected. It's getting a little ugly. Oh my god, this is so weird. Wait, what do you do if it's the right thing? Oof. Just return it. Just copy the curl response, dude. Oh my god, that's rage bait. You can't use the unique pointer. We're gonna be shared pointer. It shouldn't even be a pointer. Let's just copy it. Not even make unique, just freaking copy it. Put that bit. I don't want the pointers. So do we want the errors? So we can just return parser errors. Right? Parse result, parser parse. Vector parser errors, heap allocate. We should really just be able to do. Yeah, just make it a curl response. Copy it. Or vector of errors. Parse result. So returns a vector. Vector of derived. Treat it as base object. Parse result at parse results. I have auto lifted errors. It's gonna be. We're gonna need this. We're gonna need a vector. There. Lifted errors is equal to parse error parse to parse error. And standard unexpected lifted error. Why can I not even see what the frick? Create identifier vector. Dude, how is vector? What? Lifted errors is what I just. Hmm. We could just do this. If we do this. Yeah. Oh my god, standard vector parser. We're there, parsers. Dude, what happened to freaking polymorphism, bro? Alright, yeah, I'm not really sure what to do here. What was the problem that made me want to do all this in the first place? Yeah, trying to return a call. Hmm. Good parser. Big Yeah, polymorphism is just so annoying. You got that. Yeah, alright. So let's go ahead and end it. So if you just focus in on one example, pairs, parse error, expected header call. Bathroom. Alright, quit. It's probably about time to get back to some of the research parts of it. So actually, let me stay on this and look at what the inscription is. Dude, what the frick? Bro, frick Anduril Industries is retarded. Hobby. Alright, so the freaking whole reason I opened this in the beginning with me answer my question. Actually, just waste time waste. Alright. So we got a quiz. One sec, let me get my water. Better let me dilute my tea. So, how do turn this off? 1A. So, how do RAI sharp pointers have weeks and plus? Well, they tie the allocation and deallocation of heap objects to the lifetimes of stack objects. Or that can be indirected a bit. Perhaps you should you see in general. 1A. 1B. Can you explain move semantics and when you choose? So actually, I can't explain move semantics. So let's go. Let's go watch this video on move semantics. I actually been meaning to do that. Yeah, I don't know what move semantics are. Best off on timing, sorting, type punning. The frick is that? So I think you need this first.
R values. Sorry, is it just a zoom lens? I don't usually shoot on a zoom lens, but I am today, so I had to do that. This is going to be the first video in a series of videos which essentially is going to be talking about some more advanced C++ features, including move semantics. I don't know if this will just cover move semantics because there's obviously a lot more that this information will help you with than just learning about basically move semantics, but it is definitely a huge prerequisite for that. If you don't know what an L value is, if you don't know what an R value is especially, then it's going to be a little bit difficult for you to kind of understand how the more advanced C++ features such as move semantics work. This is definitely one of those things that is very difficult to just explain by waving my hands like I tend to do for most of my videos. So we're definitely going to jump into some code and I'm going to show you guys how this stuff works and what it is, and more importantly, why you care. But first, I want to thank Skillshare for sponsoring this video. If you guys have not heard of Skillshare yet, then you clearly haven't been watching most of my videos. Skillshare is an online learning community where millions of creatives and curious people all around the world come together to deepen an existing passion or hobby or learn something new. And unlike other kind of online communities, Skillshare is specifically curated to teach you something new. And with videos that are like super short, super easy to understand, super on point, it's a really efficient place for you to learn something new. I know that a lot of people are anxious with what's going on in the world right now. I know that I definitely am. And I think being creative and learning something is a really good way to kind of put your mind out of that and also deepen something that you might have always wanted to do. Skillshare have so many amazing classes that will teach you just so many things: photography, videography, how to start a YouTube channel and market that and start a successful business. I mean, seriously, they've even got classes on how you can like rearrange the furniture in your room to make it better. As I mentioned before, I particularly love their illustration classes because I think that artwork is something that's really hard to teach well, and I guess I just really enjoy the way that Skillshare manages to communicate all of those ideas across. And at less than $10 a month for an annual subscription, I think that it's a really useful asset to have in your library of learning. Definition for the letter L or the letter R. You just need to know what an L value is and an R value is. Don't try and kind of define it for yourself because I feel like that's a little bit of a trap. Okay, so let's start with a super simple definition of what an L value is and what an R value is. Suppose I have a variable, let's just call it I. We'll set it to 10. We have two parts to this expression. We have a left side and a right.
One sec, more water. Guys.
Right side. And this is also another good way to think about what an L value is and what an R value is. An L value is a lot of the times something that is on the left side of the equal sign, and then an R value is something that is on the right side of the equal sign. Now this does not always apply, so I'm not going to like say that this is just a complete fact. Always think of it that way because it's not necessarily true. But in this case, it is. We have a variable called I, which is of course an actual variable with a location in memory. And then we have simply a value, just a numeric literal. It's just 10. It has no storage, it has no location until it is assigned to an L value, which is what I is. This makes sense because you can't assign something to an R value. So otherwise I can't say 10 equals I or something like that. That would be weird because 10 is not something that has a location. We can't store data in 10. However, this is an L value. Now, obviously, we could just make another variable called A and set it equal to I. In this case, we're setting an L value equal to something that is also an L value, which is why I was saying that whole like right side of the equal sign doesn't always make sense. An R value doesn't just have to be a literal like this. It can also be the result of a function. Maybe we have a function called getValue, which returns 10, and then we call this function here. Now, in this case, getValue returns an R value. It returns a temporary value. It's temporary because even though it does return an int, it has no location. It has no storage. It's just returning the value 10. But what we're doing here is taking that R value, that temporary value, and storing it into an L value. Now, because this is an R value, if we try and assign something to that R value, it's not going to work. This expression is not going to work. Why? Because this is an R value. And you can see that our compiler is helping us. It's saying that expression must be a modifiable L value. Modifiable meaning it has to be non-const, and L value meaning it has to be an L value. However, this is where it gets interesting. If this was to return an L value, which we could do by returning an int reference, this is called an L value reference, then I would need to obviously provide some kind of storage for my value, maybe by using a static int like this, and then returning it. If this is the case, since this is now an L value, is returning an L value reference, I can assign to it, and this expression works fine. So that's what an L value reference is. To expand on this a little bit, if I had a function that took in a value, maybe we'll call it set value, I can call this function a number of ways. I can call it with an L value or an R value. I'll set I back to 10, and then I'll call set value with that variable. So here I'm calling set value with an L value, and then here I'm calling set value with an R value. So this is a temporary value, an R value. I keep repeating myself just so you guys really get the point here. So in this case, what will happen is this R value will be used to create an L value when the function is actually called. Now we can instantly see which one of these is temporary and which is not, because another rule is that you cannot take an L value reference from an R value. So you can only have an L value reference of an L value. And we can easily check this if I stick an ampersand over here. So now I'm taking an int reference. This is an L value reference. you can see that this immediately gives me an error. It says that the initial value of reference to non-const must be an L value. Now, you've probably noticed so far that there's a lot of mention of like const, non-const. What's the deal here? Well, there's actually a special rule, and that is that whilst I can't have an L value reference of an R value, so in other words, I can't have something like this, if it's a const L value reference, I can. So if you write const here, you can see this works. This is just a special rule. It's kind of a little bit of a workaround. Realistically, what happens is that the compiler will probably create like a temporary variable with your actual storage and then assign it to that reference like that. So really, it's just there not to kind of avoid creating an L value, but rather to just kind of support both R values and L values. Because what I can do here is make this now a const reference, and you can see that it accepts both types of data. It accepts an L value and an R value because a const L value reference can in fact accept both of them. Okay, let's scratch this example and take a look at another one, this time using strings. I'll have a first name, which I'll set to my first name, and then I'll have a last name, which I will set to my last name. Then what I'll do is I'll create a third string, which is going to be my full name, and I'll set this equal to first name plus last name, ignoring the space that I'm not adding between the two strings. So take a good look at this and try and identify what you think an L value is and what the R values are. So in this case, everything on the left side here is an L value, and everything on the right side here is an R value. So in other words, this is an R value, this is an L value, this expression here is an R value. It's a temporary object. What happens is a temporary string gets constructed from these two, and then it gets assigned into an L value. So with that same kind of rule in mind, if I had a function called print name, which took in an std string name here, and then let's just say we print it here, then if I try and call this function, print name, with full name, it's going to work fine. But if I try and call it with this expression that we had here, that's not going to work because it's an R value, which is why you'll see a lot of const references being written in C++, because as you can see, they're compatible with both temporaries, R values, and also actual kind of real existing variables, L values. So we clearly have a way to detect whether or not something is an actual L value. We can do that by just writing an L value reference that's non-const, because an L value reference can only accept L values. This will not compile, because this, of course, is an R value. Do we have a way to write a function that only accepts temporary objects? Yes, and for that we need to use something called an R value reference. An R value reference looks the same as an L value reference, except we use 2 ampersands instead of 1. So you can see what's happened here is the errors have switched now. We can't pass in an L value, but we can pass in an R value. And if we hover our mouse over here and look at the error message, it says an R value reference cannot be bound to an L value. So that makes sense. This is pretty cool because it means that we can actually write an overload of this function that accepts only temporary objects and one that accepts L values. And even if we make this const, meaning that it's also going to be compatible with R values, this overload will still be chosen if it exists. So if we take a look at our code here, I might just write L value, and then I'll do the same thing over here, except I'll write R value. If we now call all of these, and I'll just do a little std_scene.get so the console doesn't close, you can see that the first overload that was chosen was the L value one, and then the second one was the R value one. So this is all really cool, because with R value references, we now have a way to actually detect temporary values and do something special to them. So the question now might be, well, okay, but how is this useful? And the answer is, well, it's very useful, especially with move semantics, but that's going to be a topic for another video. Basically, the main advantage here is to do with optimization. If we know that we're taking in a temporary object, then we don't have to worry about making sure that we keep it alive and making sure we keep it intact, making sure we copy it. We can simply steal the resources that might be attached to that specific object and use them somewhere else, because we know that it's temporary. It's not going to exist for very long. Whereas if you take in something like this, then you can't, I mean, apart from the fact that it's const, you can't really steal anything from this name string because it might be used in a number of functions. Whereas this is clearly something that is temporary, only going to be used with this particular call of print name, and that's where the power really comes from. So remember, L values are basically variables that have some kind of storage backing them. R values are temporary values. L value references can only take in L values unless they're const, and R value references only take in these temporary R values. Anyway, I hope this video, sorry, I'm just playing with the paprika. Hope this video made sense for you guys. As I said, definitely one of those topics that a lot of people are very confused about, so hopefully this video helped to kind of Hey, what's up guys, my name is Eterno, welcome back to my C++ series. So today we're going to be talking about move semantics. This is probably like the single most requested topic, so I'm happy that I'm finally getting to it. And today we're going to be more or less taking a look at an introduction to what move semantics is, because it's a very complex topic. The basics is really simple, but then what you can do with it and how it works in practice, we'll get to that stuff, don't worry. So first of all, make sure that you've seen my L values and R values video, because this is more or less going to be a continuation of that video. Now that we've learned what R values actually are and what R value references actually are, we can take a look at their single biggest use case, move semantics. To keep things simple, move semantics essentially just allow us to move objects around. And this wasn't possible before C++11 because C++11 introduced R value references, which are necessary for move semantics. The basic idea is that when we're writing C++ code, there are a lot of cases in which we don't really need to or want to necessarily necessarily copy an object from one place to another, but that's really the only place that we can get it from one place to another. So for example, if I'm passing an object into a function that then is going to take ownership of that object, I have no choice but to copy it. The same goes for when I want to return an object from a function. I still have to create that object inside that actual function and then actually return it, which means that again, I'm copying that data. Now, I don't really like to use return values as an example for this because there is of course something called return value optimization, which can kind of optimize that part of it and make it less of a problem. But with the first example, if I need to pass in an object, a new object that I'm constructing into some kind of function that takes ownership of it or whatever, I still need to unfortunately construct like essentially a throwaway object in the current stack frame wherever I am, and then copy it into the function that I'm calling, which is not ideal because I don't actually need it here. I need it there, but I can't construct it there because I need to first construct it here and then pass it in. It becomes a huge mess. And sure, if your object just consists of like a couple of integers or something like that, then copying it is no big deal. But what if your object needs to like heap allocate memory or something like that? Like what if it's a string and if you need to copy it, well, you need to create a completely new heap allocation. That's not good. That becomes a heavy object to copy. And that is exactly where move semantics comes in. If we can just move the object instead of copying it, then our performance will be higher. And I promise you, once we dive in and take a look in a minute, you'll see that this is not nearly as difficult as it might seem. But first, this video is sponsored by Skillshare. For those of you who don't know what Skillshare is an online learning can by clicking the link in the description below. Huge thank you again to Skillshare for sponsoring this video. So, move semantics. Let's dive in and take a look at what all the fuss is about. Let's write a class that's going to serve as an example to demonstrate why exactly we might want to move something. So I'm just going to write a very basic string class that might look something like this. This is not by any means going to be like a proper way to write a string class. In fact, I might make a video on that sometime in the future, but let's just say that we have a class which has a char pointer of data as well as some kind of size. This is our actual string data. So what we want to do here when we take in a const char pointer like this is essentially set the size to be the string length. So whatever the length of this string is, that's how many characters we might want. We probably want a null termination character as well, but we'll just skip that for the purposes of this example because again, this is about move semantics and not necessarily about how to write a proper string class. And then into here, I'll just do a basic mem copy to move all of the data in from the source string here into our data buffer. So now that we have that, and I'll actually just add a little printf here, which just says created, just so that we can later visualize our kind of code flow. So we have a basic constructor here that takes in a string and allocates memory and copies everything into that memory buffer. Now, inside the destructor, we might have something fairly simple that just simply deletes the data. And that's about it. That's our basic string class. Now let's write some other class. For example, maybe I'll call it entity. That's basically just going to consume our string. So inside the entity class, I might just have like a standard kind of const string reference here. Maybe this will be like the name of our entity. And then obviously we will store this. So I'll just write string mname here. And then I will simply just assign it like this. So at the moment, for this to actually work properly, we need to write a copy constructor, because if we just simply create a string over here, or in fact, let's go the easy way, I'll just say entity, and then maybe call it cherno like this, and we're using the implicit constructor here, so really what's happening is that, and I might leave it like that for clarity. But basically, if we just have some code like this, we still need some way of copying this string into this string, and so we need a copy constructor. So what I'll do is I'll write a copy constructor here, and this copy constructor is going to be very similar to this constructor. I'll copy it, in fact. I'll just change this to copied, except obviously the size is just going to be other.size, and then everything else is pretty much the same, except of course we just write other.mdata. So now we're just copying the string, and we have a valid way to actually get it in here. If I run this code, in fact, let's do one more thing. Let's just write a function called print name here, and then that needs some way of printing the name, which we can't actually do at the moment. So let's write a very basic function here called print. Now, because our string class is special and doesn't have a null termination character, what I'll actually do is loop through the size of the string and then print each character one by one. C for char, and then we'll do mdata I, and then at the very end, I will just print a new line character. So now this will just call mname.print, and we should have a very basic program now that will just basically just print cherno. And if I run this code, you can see that we have created, copied, and cherno. So everything is in fact working. However, this is really the problem that we're addressing today. We have this copied line being printed, which of course means that our data is being copied. Now, why is this a problem? Well, the reason it's a problem is because you can see that to copy a string, we need to allocate memory on the heap. We have to call new char. That's not a good thing. It's definitely not terrible, and especially if you have just one copy like that. Let me just quickly add this thing in here as well. It's not necessarily like the worst thing in the world, but remember, the fact that we have to copy this is a little bit ridiculous because, I mean, look at what we're doing. We're essentially creating an entity called cherno here, and I mean, we just need some way of getting the string into here. And what does that do? Well, that has to allocate memory twice because we need to create it first in the scope of this function inside our main function, which is what happens over here. We're actually creating it inside the main function, and then we're passing it into this entity constructor, which then on this line over here has to actually copy it into here. Why can't we just move it into here? Why can't we just allocate the memory right here and just have it there? Or, I mean, worst case scenario, because we can't really do that without getting access to this string and then doing stuff like that manually, why can't we just still allocate it here in the main function, but then just move it into this space? Because now we want it to occupy this space. And the answer is, of course, we can. And that's where move semantics comes in. So what we need to do in this case is write a move constructor. So this is very similar to the copy constructor, except this takes in an R value reference, meaning a temporary. So this right here is a temporary. It's not an L value. It's not assigned to anything. It's just used up as a parameter for this actual entity constructor. So now by specifying this constructor, which by the way, we should specify with no except. I mean, even Visual Studio is telling us because it's not really supposed to be throwing exceptions. Not that we really use them anyway, but just to be ultra correct, we'll do that. And by specifying this constructor, the hope is that eventually when we actually perform this copy, instead of copying, it will actually move. Now, in order for that to actually work, we need to also make sure that entity has a constructor that takes in a temporary. So instead of kind of doing that, what I'll do is I'll actually copy and paste this constructor. So I'll just add a new constructor that takes in a temporary like this. And our hope, of course, is that when we actually call this, because now that this is a temporary and we're providing an R value reference constructor, since this is an R value, it will actually call this constructor now instead of this constructor. Now they are both the same. They do the same thing. They just assign name the same way. So nothing will change, but that's kind of the first step. So now we need to actually implement our move constructor. So what I'll do is I'll copy, in fact, I'll just copy everything and I'll show you how to do this. So we'll say moved over here. Size still gets copied the same way. And what we'll do is we'll actually copy data. But what we're doing here is instead of actually allocating a new buffer of data and copying everything individually, copying that entire block of data into this new block of data, what we're doing instead is we're simply assigning the pointer. So we're taking the pointer to mdata, which is the pointer to the existing buffer that we had in our original string. And now we're saying that this pointer that we have here in this new string instance that we've constructed, it actually points to the same data. So instead of allocating an entire new block of data and copying everything into it, we're just essentially pointing to the same block of data as the old string. Now this immediately presents a problem because we do still have two string instances. So what happens to the old one when it gets deleted? Well, it's going to take the data with us. So what should we do? And that's exactly why a move constructor cannot end right here. You have to also take care of the other string instance, who you're basically taking control over. You're stealing all of that data. So to do that, we need to also assign mdata to null pointer. That's kind of the major thing that we need to do. But also what we should do is assign size to be 0. So by doing so, we've basically created something called a hollow object. This old string is now essentially just in kind of like an empty state. And what will happen is when the old string instance gets destroyed, this delete mdata will actually be deleting null pointer. And obviously deleting null pointer just doesn't do anything because there's nothing to delete. The pointer is pointing to null. So we've effectively just taken over that old string. Instead of doing a deep copy by copying all of the data and allocating new memory, we've essentially done a shallow copy. We've just kind of rewired the pointers. So now everything should be good, right? Let's run this and see what we get. And you can see that interestingly, we have created, copied, destroyed, and cherno. So interestingly, the cherno is being printed after destroyed because that's actually our temporary getting destroyed. So that seems to have functioned. This didn't crash or anything. However, we still have a copied, which is a little bit odd because, we provided this constructor. What's going on? And the final answer is that what's actually happening is the copy constructor is still being called over here. When we actually assign a name like this, it's actually still using this constructor. To get it to use the move constructor, you have to actually explicitly cast it to a temporary like this. And if we run this code, you'll see that we have a moved now instead of copied. So we've successfully only allocated memory once and managed to move the string into the entity class. Now in practice, you wouldn't really cast it to an R value reference like this. Instead, you would use something called std_move, which essentially does the same thing, but we'll have an entire video on std_move and all the stuff that's used for in the future. So let's run this code and you can see that we still have the same result: created, moved, destroyed, and then we managed to print our string successfully. Everything seems to run. So the major point of this is that we've saved using this copy constructor to actually allocate a new block of memory and copy it. We've simply managed to move that instead. So we still only have a single allocation, which is great. Okay, so I hope that was somewhat of a good introduction to move semantics. Of course, there are so many more things we could cover, such as std_move, and don't worry, we will in future videos. But I hope you guys enjoyed this video. If you did, please hit that like button. Don't forget that you can try out Skillshare free for 2 months by clicking the link in the description below, and I will see you guys later. Goodbye. Hey, what's up guys, my name is TheCherno. Welcome back to my C++ series. So today we're going to be continuing on with our whole move semantics journey. If you guys have not seen the other videos in this kind of little mini series, then definitely check them out. I'll have one linked up there that's going to be about move semantics in general, but there's also another video about L values and R values. So if you're new to this whole moving journey, make sure that you check those videos out because they're going to be important for what we'll be discussing today. So far we've basically learned the gist and all of the basics of move semantics, what it means to actually be able to move one object into another. However, we haven't covered a crucial part of that, or should I say 2 crucial parts. And instead of making 2 videos, one on each topic, I figured I'd combine them into this video because they're not particularly complicated topics, and I think we can just get them done in one video. And that is std_move. So what is that function? What does it do? When do we use it? When do we need to use it? And then also something called the move assignment operator. And this is specifically an assignment operator that we use when we want to move an object into an existing object. So we've covered move constructors, or a move constructor. That's what we did in the last episode. However, what we haven't covered is what happens if we, instead of constructing a new object, object, we want to move an existing object into another existing object. And that's what we're going to be talking about today. But first, this video is sponsored by Skillshare. If you guys have not heard of Skillshare, Skillshare is an amazing entity move while doing that, since that's an important part. So this is the string class from the last video, and here's our entity class as well. Let's first talk about std move and what it does. I'll actually use string as an example here, just because we seem to have this kind of, we have two classes. We have string, we have entity, and entity is like an extra level of interaction. Entity itself, in fact, is an example showing how to use string, which is the real thing we're interested in moving. So what happens here when we decide to actually take in a string as a temporary here is we're using std move. And this is from the last video. We had to use it because this was a way for us to move this name temporary, which we're providing over here, into this kind of more or less permanent spot for it to live in. If I simplify this by writing it over here, I'll create a string and I'll just set it to hello over here. So now I have a brand new string. What happens if I want to move it into here? Maybe this is the destination for my move. Well, I could assign it like this. However, what that's doing is copying the string into this new destination variable, of course. So what do I do if I want to specifically move it into this new variable? Well, I have to make it into a temporary, because that's what the move constructor takes, right? If we look at the string constructor here, we have this one, which is our move constructor. This takes in an R-value reference, which is a temporary object. So in other words, it's really simple. I have to make it use this constructor, because this little blob of code here is what actually steals the resources from other. So in other words, that's the thing that actually does the move. So in order for it to use that constructor, I need to actually make sure that this string, this hello string, becomes a temporary now. And how do we convert from one type into another generally in C++? We cast. So what I could do is I could cast this to be a string temporary like this. And what's happening here is it's now constructing a new string with a constructor that takes in a string R-value reference here. So in other words, this is the same as if I had just written code like this, because of course that assignment operator is just doing an implicit conversion and call into this specific string constructor. So this is the code that I end up with. I'm now moving this string into this new destination. However, this is a little bit well, it's not the most elegant way of doing this, and it also doesn't work with every single type. For example, if we just had something that was auto and the type couldn't be deduced by ourselves writing the code statically like this, it's just not a great way to actually write code like this. So what we do instead is we use a slightly more flexible function that basically at compile time figures out what type is coming in. And that function is called stdmove. So what this is just a utility function provided to us by the standard C++ library that will basically do what I just did, but in a slightly more elegant and flexible way. If we hit F12 over here in Visual Studio to get to it, you can see what's actually happening here. It's a const expression. It returns a remove reference t type of ty, and you can see there's that R-value reference here. So it takes in an argument here, and it will actually return that double reference for us. But it does so in a nicely templated way, and it will work properly with all types, including const and all of that stuff. So instead of doing what I did, you should use stdmove. And it also looks a little bit more elegant in my opinion, because it also gives a little bit of context as to what's going on. In this case, we're moving this string into this destination. Now, I want to emphasize here that it doesn't really matter how you write this code. I could just have an assignment operation going on over here. The thing is, we're creating a new object here. This is not a move assignment that is taking place here, because as you can see, we've got the variable type out front here, and then the variable name. This is a brand new object that is being constructed, and as such, it will actually use the move constructor. Now, this leads into the move assignment operator, which is what I talked about. An assignment operator, which I don't think we've covered in general in the C++ series, so that's definitely something that we'll do soon. But the assignment operator only gets called when we actually assign a variable into an existing variable. So in other words, if we now wrote something like dest equals string or something like that, or more specifically stdmove string to actually move it, in this case, what would actually happen is the assignment operator would get called, because this is already an existing variable. Don't forget that an operator is really just like a function. And so when you actually call the equals kind of operator here, which is the assignment operator on an existing variable, it's kind of the same as if you just had like a little assign function and did something like that. Clearly, this is happening on an existing variable, whereas over here, like it wouldn't really work because we're creating a new variable. So let's go up and define this assignment operator. So a regular assignment operator is something that we'll say for a different video, of course, because this is about the move assignment operator. But basically, it's going to be very, very, very similar to the move constructor. So this is going to be a good starting point. What I'll do is I'll just copy all of this stuff here, and then I'll go down here and write string reference. So this is going to return a string reference. We'll write operator equals, which is our assignment operator, and then it's going to take in that temporary object here. We'll also mark it as no accept. I'm going to paste in all of our code here, and for the most part, that is basically it. However, there is one very important thing missing here. What we're doing is we're not actually constructing a new object like we were in the move constructor. We're actually moving another object into ourselves, into this current object. So clearly we need to actually overwrite the current object, because the current object might have some memory allocated. And obviously if we just do this, if we just set mdata equal to another pointer, we've created a memory leak because there's no way for us to actually delete that old data. So what we need to do is, first of all, delete our current data because we're about to move another object into ourselves. And then we can reassign all of our variables and also make sure that the other object is left in a valid state. So this is basically the most important thing that we can add. Now, typically in assignment operators, you also want to make sure that this current object is not equal to another object. So in other words, if we try to do something somewhat silly, such as assign destination to itself using something like this, right? Or I guess more specifically, we'd have to put it into here. If you try and do something like this, then this will not really work because obviously what we're doing here is we're deleting data and then we're just reassigning everything. I mean, what's gonna end up happening is we just delete the data and we've lost the data and that's it. Size will still be kind of correct though. So it's in general, it's just gonna mess everything up. What we could do, and specifically the right answer here, is to just not do anything in this case, because if these objects are equal, then there's no moving necessary. I mean, you're trying to move this object into itself. It's already there. There's no moving necessary. And the way we would typically implement this is just by saying if this equals other, just like that. And if you do something like that, and specifically does not equal is what we want, if this is not equal to other, so in other words, these are in fact different objects, then nothing needs to be done, and we can just return this, which is a reference to the current object. So in other words, we only do the move if they're not equal. If they are the same object literally, then we don't need to do anything. If they're different objects, but the data is different, you still need to do the move because you're still moving some other object into yourself. So this isn't really like the assignment operator where you're doing a copy, and if the data happens to match, you don't need to do anything. So you still need to do it, and it's very easy to just implement a little guard that does something like this. So there we go. That is a complete move assignment operator. Let's test it out. So what I'll do is I'll make, and to actually make this work, we do have a default constructor for string, which is good. We're going to kind of ignore the entity class for this example, I think. And what I'm going to do is basically come over here and I'll make a string here called, well, this will just be like our first string. I'll just call it apple and I'll set it equal to apple. Then I'll make another string called our kind of destination, which is just going to be an empty string here. And then what I'll do is I'll try and actually assign destination to be apple. Now, obviously this is going to cause an error here because we don't have an actual copy assignment operator. So what we need to do is make sure that this is wrapped in a move. Otherwise it's not even going to compile. And what should happen here is we should move the contents of apple into destination and also leave apple in a good state, in a valid state. So let's print the value of both of these. I'll call apple.print and then destination.print here. And I'll also do so after we do the move. And we'll see if the values have basically switched. So in other words, since we're stealing everything from apple now, it should be left with nothing. And we shouldn't get any crashes or anything, obviously, upon destruction. Okay, so and there's some other stuff going on here, so I'm going to quickly get rid of all this other noise. Okay, so we have created, then we have apple, and this is, I just realized that what I should also do is make sure that I'm actually printing the value of these variables, or rather the name of these variables, because at the moment we're only seeing the actual values. Okay, so now if we run this, we create the object, apple is set to apple, destination is set to nothing at all. Then we move it, and now apple is set to nothing at all, and destination is set to apple. So we basically transferred ownership of that entire array of characters without doing any copying or any allocating or deallocating or anything like that. We've switched these two variables, which is really good and amazingly powerful. And that's it. You can see both of the objects get destroyed successfully. We don't get any crashes because in this case, the apple destructor is doing absolutely nothing since it's trying to delete an array over here that is set to null pointer. And then the destination destructor is destroying our characters successfully. So that is the end of the move assignment operator and std move. So in summary, the move assignment operator is something that you want to include in your class when you include a move constructor, because of course it might be desirable to move an object into an existing variable. It's basically part of something called the rule of fifths. There's something called the rule of thirds, and then there's the rule of fifths, which basically just includes all the new move semantics things. We'll talk about that more in depth in later episodes of the C++ series as well. One more thing I quickly want to show is that I did mention the difference between destination and the assignment operator versus if we had just used the constructor like this. Keep in mind that by using this operator, it is literally the same as if we had written dot operator equals and called it like a function, which is why clearly that would not work here because we're not actually calling the assignment operator. We're just constructing a new string that happens to use a temporary value, which is why the move constructor is being called. Whereas here, we're actually calling a function. So that's an important distinction and one of the things that used to confuse me in the past, because as you can see, they both look like assignment operators, but they're actually different. This is the move constructor. This is the assignment operator. And std move is what you want to do when you want to convert an object to be a temporary. So in other words, if you need an existing variable to become temporary in the sense that you're basically marking it as, hey, you can steal resources from this particular variable, this is what enables us to actually do the moves on an existing variable. If you're creating a new variable and it's like in a function parameter or in the move constructor or something like that, then it's already a temporary, it's fine. But if you've got an existing variable, like with this apple example, that was an existing variable, you need to make sure that you use std_move to basically convert it into a temporary. And then that way you can actually use the move constructor or the move assignment operator to take the resources from that variable and actually do the move. Hope you guys enjoyed this video. Please don't forget to hit the like button if you did. If you have any more questions about move semantics,
All right. I gotta go to the bathroom again. Abby. All right, so can I actually answer this question? Can you explain move semantics and when you choose to implement? Move semantics? I don't understand what the semantics part is. Like, what is the semantics? Move semantics allow an object to be moved into another one, whether that's one that already exists or one that you're constructing as you move things into it. I choose to implement move semantics are implemented with the move constructor and the move assignment operator. The move constructor for the case where you're moving into a new object, and the move constructor where you're moving into an existing object. I choose to implement them when I choose to. So at the most basic case, if you want to construct something from an R value, convenient to make them. I want to construct an object from an R value without a copy. Reuse an object members a different object. I mean, yeah, that's not the best. Okay, 2A. There's a difference between processes and threads. Well, from a Unix perspective, there's no difference. There's little difference. Processes have their own code, have their own have more of their own data structures. Threads share data like file descriptor. Descriptors code from the process they were forked from. Still have their own stack though. How do context switches impact performance? Context switches hinder performance. Context switches occur when hardware. That's a bit ambiguous. When a processor overwrites the working registers of one process, asked to run a new one. Process takes time that could be spent actually making progress on a task. 2B. How does virtual memory work, and why is it critical in modern applications? Virtual memory works by providing processes with address spaces that do not map physical RAM. Instead, they do not directly map to physical RAM address. Instead, to virtual address map to physical. This indirection allows a few things. One of them is you can use disk, or you can have so you can have process memory in non-contiguous, or in what appear to be blocks of contiguous addresses, but they do physical that are not, produces fragmentation. You can load process pages disk off. But what else does this indirection of virtual memory? It allows processes to write, not to, or processes don't need to worry about what absolute memory address right to. They see the mem start at 0. This 0 is relative to the that. Physical header the page maps towers don't need to worry about shifting the red. It's crucial for modern application to fragmentation, allow code sharing, CPUs have relatively few processors, on the cores, and threads execute. They have mini caches, 3, really. And are closer to memory in general. GPUs Around a dozen. Red. Has a relatively high clock speed. Clock speed. Power consumption. CPUs have thousands. Fusion. More caches. And less of them. Lower power consumption. Core. Clock speed. 3D. How do you optimize code for cache performance? What role does memory hierarchy play? You optimize code for cache performance by accessing memory. Cache performance is influenced. So I know what you try to do. So you try to overwrite stuff that you're going to use. When you overwrite something in the cache, you want it to be something you're not going to use. When you load something into the cache, you want it to be aligned on your architectures. Excuse me. Bit depth. Word length. So by aligning data structures, align data structures on multiples of your arc's word length, so you don't need to shift or access multiple words. Data. By using adjacent memory addresses for an adjacent time. This way, the probability that data isn't overwritten in the cache. Can optimize code for cache performance by running same scheduling the same process on the same CPU thread. This this decreases context switching, increases probability of the cache having data from your process. 4A. How would you design a system to automate GPU asset provisioning across multiple cloud providers? I don't even know what that means. Yeah, how do I do that? How do I do that? How would I design a asset? So asset provisioning. So you have an amount of GPU. Cloud providers are like AWS and all. So if I have these, I want them to access GPU. But I have a system of jobs. Cloud providers. So I'm not really sure how it works. Cloud providers have jobs. Could you give me some more? Do the cloud providers run jobs that we could perhaps queue? Or is it more like the SSH into a has and or B? What challenges arise in building fault-tolerant distributed systems? So, fault-tolerant distributed systems apply replication, same service. Perhaps that service is a web service. Get back. Service. VN. A database. Here are some challenges for you. So, backend web service is the easiest. It's the least challenging. Replicate. Assuming that it doesn't have much state. Process requests that come to it. A load balancer and manage distribution requests to these backends, and they can be replicated without much trouble. Load balancer adds latency. If you didn't have your servers would be poorly unified. With it, it's too hard. So in the case of a CDN, CDN caches content locally to where it's being requested. Traffic elsewhere. It's really a solution to this isn't really about the fault tolerance. I'm not gonna talk about that. It's not really about fault tolerance. Another fault is the hardest part related to database. As soon as you scale a database, you have to worry about many things. One is the consistency data between DBs. You write to one at the same time, read from another. Or sorry, right before. You've read stale data. Fix it by scaling your DB. Sharding doesn't duplicate data. Let's separate, divide. Yeah, I read maybe designing data intensive applications, but I lucky forgot what all the other tactics. Another. So it's like the CAP theorem. What is the CAP theorem? Consistency, availability, and what is CAP? What's the P? It's like 2 words. Theorem. Partition tolerance. Okay, I needed more. 5A. The typical challenges when developing firmware data center hardware. Bad documentation. Requirement to comply with many API protocols. And having to use Google API, Amazon API, NVIDIA API, different versions of the same thing. Changing API to data center. 30. I don't know too much about that. Describe your approach to debugging and optimize low-level debugging. I don't think my approach is very unique. Any different than anybody else. Low-level system software. Debugging. Visual C++. Fucking C++ terms. Approach to debugging. PDB. More likely. Custom logger. Terminal. Not embedded. I'd use print. I'd use breakpoints. Prints. And copy and move constructors. Analyze memory performance. Add benchmark functions. Speed performance. I'd analyze the cache. Just cache coherence mean? Oh yeah. I'd analyze the bit rates. Not that I've ever done that. Or no to do this. And consider whether my data structures are well aligned could be used orally, facially. Not too sure on 6A. Robust testing. Robust testing. So good telemetry. And things wrong in the first place. But yeah, I don't know. Question. How would you implement CI/CD for a platform that bans from hardware firmware? AI. Well, how would I do this? So hardware firmware. So start have a solid testing throughout that trigger workflow date patients. I'd have secrets somewhere. Alright, that's not really worth. I'd then build. Oh. Build environments. Define reproducibly. Something like Nixflakes. You gotta throw that in there. Like Nixflakes. So for hardware firmware, I'm not sure. Hardware firm. What is hardware firmware? Because firmware software. Firmware really depends. Used. But perhaps we have workflow on the servers running Linux. We apply a patch to the kernel. We do rolling deployment. Imagine we have server racks, GPUs, update a few, like 1% of them, analyze telemetry, and scale over time if successful. If I patch the kernel to the AI infrastructure, in my mind is like system. Do the same. Update microservices incrementally. Use load balancers to send small but increasing amounts of traffic. Telemetry does well. Scale up until we've fully formed. Cache the previous state of each of the kernel patch, previous Docker container, ever. so that we can very quickly roll back. Need 7A. Given an increasing load on AI infrastructure, how would you approach scaling the system? So I really can't visualize AI infra to, like, what is AI? What is AI infrastructure? And be not as intern elsewhere. I did soft infra and in personal knowledge, hardware, software, but free. But probably answer literally just more node traffic. Yeah, I don't really like. How do you? I don't think there's a ton of. I'm not certain of a ton of answers. Given an increasing load, say we're at this like GPU and we just have more load. Yeah, we just make more nodes. Like I don't know what to say there. I feel like that's obviously, or that answer is like good point. One B. So how do I? So I should have said more about the lifetime. I guess. I guess it is really not just stack objects. That was kind of. Can you explain move semantics? Oh, yeah, move semantics with decoding improvements emphasize that after a move, the source objects remain in a valid but specified state. I also mentioned operating system concepts. 2A. Dude, tell me what the concept is. You really want me to describe the difference between processes and threads, and then how is it directly differentiate process and threads? Processes are isolated, have their own address space. Threads share memory. I mean, they do have their own stack. Adding an example or quantifying overhead. Okay. And then virtual memory. You cover the benefits of virtual memory. Also provides memory protection between processes. Good point. But also talk about TLBs. Yeah, that's good. So 3. The CPU versus GPU and cache performance. High level differences. GPUs are optimized for a single instruction, multiple data. And cache. Data alignment, cache blocking, prefetching, algorithm mode. So tell me more about 3B. So yeah, I don't know what that is, so tell me. 4B, 4A, 4B. Oh yeah, how would you answer? What's replication? Eventual. Yeah, I remember eventual consistency from the book. We just forgot what happens. That's why I don't listen to things as an audiobook. The firmware, yeah, I was already. Interoperability issues, version management. Might be. Favorite approach debugging. Valgrind, Perf. I should use Valgrind on request just to say I've done it. Root test, static analysis tools. Yeah. Fix robust testing and CI/CD for AI. Telemetry. Logging system with order thresholds. Distributed tracing depending. And then test framework. Blue, green, canary deployments. Yeah, what are canary deployments? I know we did that. I forgot what that is. That's what I said. Blue, green. What is blue, green? That's where you have one and you roll back. Load balancing, horizontal scaling. Yeah, okay, horizontal and vertical. Latency and redundancy. Alright, so I gotta do the bathroom again. You know, I've been drinking like 40,000 things of water. So. Okay, so let's see what Buddy said. Optimizing code for cache performance. So let's actually download Valgrind, Loki. Let me get a NixOS Valgrind. Get the whole Valgrind. Valgrind. So it's gonna be kind of annoying. Put a mem check. Okay, that's into my make list down here. Paste that. Your execute. Yeah, that was very dumb. Target file. Image just target. Okay. I'll heap box for. But then it still errors, man. That error. Error summary, 0 errors. Make memcheck error 2. Huh? Oh. Working directory. And C-test. Do I have C-test? I think I have C-test works. C-test. Memcheck. I'll have Dart. Ninja. Use CMake with a ninja. CMake dash ninja dash worship dash. Where the CMake hat? You did a dash build dash dar build dash b build. Just be build. Ninja. On speed, I mean. This. This is gonna take a while because I deleted all of that. Deleted the fetch contents. Cache blocking. So break large data sets into smaller blocks that fit into cache. And matrix multiplication. Operate on the submatrix So that once a block is sort of cache, it's yeah. Prefetching. Use prefetching to load data into the cache before it's needed. Software prequesting can be done using entire redesign algorithms to access memory sequentially rather than data structures for contiguous storage, boost spatial locality. Cache thrashing is when a bunch of like two data structures map to the same cache set and they keep evicting each other from the same set every time. You can resolve this by aligning the data structures on cache line boundaries, perhaps padding them and optimizing the data layout. So designing a system for GPU asset provision. So quick requirement first. What APIs manage? So an API that normalizes interactions with different cloud providers. AWS, GCP, Azure, etc. So the underlying differences are hidden from the GCP. Azure has a service things. So an API kind of around. Central service that monitors cloud queue. Provisioning. There's another here. So after that, you just run Ninja. Dash okay. $14 on the system. Holy 220. This I'm gonna run out of RAM, bro. Okay. What for? So if you want to do it here, enable testing. Test dash T. Dog, what is memcheck? What ninja test? Go. Ninja unbound. Test. Do this test mem. I also write these commands. Elements of test. Fix develop. Commands. For anything. Build and enter a development environment with tests. Teammate. That Bash script. What's this? Tests. Not find a freaking Dart config. Dog, what is a Dart configuration? Oh, what? Just action. Not find file Dart configuration. Food seed. Again. That's no. I think it's running out of my test and I'm where's my Dart config? Where's it not running it on my I want to do Valgrind. What was the last Valgrind? Oh, it's good. They're still just running tests. Recheck. I don't want to know my tests. Test. Let's see anything. How did I just do the thing where I checked my junk, bro? Let's just test your. Is that's dude. That's what I want. Such examples. Get some errors. Huh? Oh, it's because the weak check full was breaking. Okay, so let's clear that. Conditional jumps versus First run. And the deadlock hit. So what I want is that to run. West. Mag. Read me. Do that. Best test. Just West. Grand. East. Grand. Can we run from builds? Gonna be editors. But does it work if I do stock? Oh no, that's dash examples. Dash I. That's my command. 71 errors. Womp womp. Get that. Just get ignore. And let's see. Your CMAX. Your CMAX. Build. British You just run. So sudo apt get install ninja, I guess. Me and CI grind got 109 errors. Does build though. But yeah, the perfect. Conditional. Alright, so back. That was a nice little detour. Back to this. Streaming for kind of crazy. Depend based on policy that cost your application. Here's API telemetry. Security file type. Data consistency, latency. Gracefully, so you get replication lag. Random. Asynchronous application. Data. Mitigation. Or design this is. Central consistent. So updates are propagated to immediate for high availability and consensus. Implement consensus algorithm, Paxos or Raft, state change reliably. Protocols reaching agreement even quorum based. Reads and writes. Majority of agree on an update. Independenent operations so hang them because states and states. Swap man. Fault isolation of breakers. Isolate failures using techniques like circuit breakers. Okay, whatever. 1. How do you decide between using a standard vector and a standard list performance critical code, and what is memory? I don't know what standard list is. That's good. Container that supports constant time insertion and removal of elements from anywhere in the container. Fast. Usually, it does it. For this. Vector is an array. List. Make the list. I'd use a vector. So I'd use a list. To commonly add and delete the first or if effect to resize big to small. I want to access random vector. Append of my copies. List all. List is also this. That's needed. Describe how you would implement a thread safe queue. Let's pause and discuss the thread safe is what's for agent type def type name. You can either enqueue, dequeue. Let's make it fact standard list. The members of the queue be immutable with mutex. Okay, you need the mutex. For the enqueue function, start by not lock guard, but lock. What's the other? Up to the line. List. Respond in the list. Then increase size. Here. Okay. New tag. Then add this back. Is that a thing? Hop back. Director list. Destructure. Free the list. And do move. Do copy. Copy and move directories. But the features like const expression and function comments plus. Oh. Const expr evaluates values at runtime. Can make faster by moving performing calculations that are not dependent IO. Runtime. Code size. Inline can be fast by subverting function and content inline. This could be faster. When is inline faster? It does take also allows addition. Deaths. Not the best. So how does the OS manage CPU scheduling environment? So in a multi-core environment, For instance, Linux uses the completely their scheduler handles multi-core via thread safe access to a ready queue that discriminates based on what threads the task was already ran on to thrashing across context switches. You can optimize CPU bound tasks, context switch setting longer. What's that called? Like eviction time? In IO bound tasks by context switching more often, but giving them less runtime each time. By minimizing conversation, it's giving more runtime. 5. Distributed GPU provisioning architecture. Outline a high-level design for a system that automates GPU asset provisioning as preferred. I thought we just did this. So, cloud providers. Dude, we just made the message about not making this so broad, and then you just make it so broad. Broad. But stop asking very broad questions that obviously require a conversation of follow-up. Clarification in this format. Be more specific. Oh, I accidentally pressed enter. Dang it, I was really good about shift entering for a while. Vectors contiguous storage improves cache locality and this offer cost and time insertion deletions, but with pointer overhead, potential cache miss. Let's save Q. Using a condition variable so that DQ can block when in. Okay. That's a good point. Well, yeah, I mean, obviously, if you back it with a Q. Vector-based approach, you'd have an index for the beginning and end. Often auto inlines functions. That's literally what I noted, bro. Scheduler adjusts time slices based on past CPU usage and priorities, balancing performance between ground chat. For feedback. Yeah, I know, but if we're doing 9 questions at once, I'm not trying to have a conversation while I'm in the middle of answering all the other questions. Like, bruh. So, in a performance critical application, how you decide between using standard vector standard deck. Well, I mean, using a standard deck is kind of. I wouldn't use standard list at all. And efficient versions deletions. Well, I guess yeah, list is actually trash. No, list is trash. Yeah, list was dumb. Because the whole appeal of list is like inserting into the middle and constant time and shit. How would you implement a blocking deck operation? Or I guess it wasn't. Was mine double-ended? I guess you could double-ended. How'd you implement a blocking DQ operation deck? DQ operation. Deck DQ operation. In your thread safe. You design using condition variables. So I'd have a condition variable. Yeah, I don't know how to do that. Can you provide an example of where using constant expr in a recursive function? Yeah, I mean constant expr, if you know what n is going to be, if you want to know what the nth Fibonacci, while you use your compiler, if your function is constant expression, it will put any reference to this, whatever you call n, it'll just fill in whatever that is. That's more performant because you're doing all that, not a runtime. And how the CFS allocates CPU time among processes. It uses like a multi-level feedback queue. How do adjustments in time slices affect the performance of CPU bound versus IO bound tasks? So time slice being shorter makes IO bound tasks happier because they're more responsive CPU, but longer better for CPU bound because there's less context switches. Design a unified API for GPU asset provisioning that abstracts over different cloud providers. Provider specific authentication with OAuth. So how would you answer 1, 2, and 5? So also, let me do my assignment. Lipstick face. Alright, so I need to start thinking about doing meat code. For 5 hours.
Hands on the hanged up, Loki when she hanged in the
This might be my longest stream, bro. 10 hours. Just a dude sitting here for 30 hours. It's insane. I'm not even tired either. It's not even because there's caffeine in my tea. Because there's not caffeine in my casual 12-hour stream. They do, bro. Interviews, one of them has. We're not gonna insert in the middle of a queue. So. Walk until it's not empty. Oh, he's talking about a literal low that That enough random? Yes. Okay. Let's do. I feel like I need to do Ecode. So annoying. Like really. Alright, so it really is time to do Ecode. Alright, why am I complaining? Big cringe. But how do you these questions? Can you search these? I didn't even get an LA, bro. Medium to hard. Ecode hard is crazy. Alright. So let's kind of rotate through Cherno, the last bit of Cherno of this book. At this point, I think I'm good. I'm reasonably good on the well, first off, let me go back to the job. Ground grid system. Automates GPU. Cloud provider. Design developed the center. Okay. Closer to the hardware software infrastructure. Server level reliability. ESP. Failure analysis. Okay. So I feel like I should do some leak code. Also some questions like the queue. And some questions like implement unique pointer. Let's start with just for sum. Given an array nums of n integers, return an array of all of the unique quadruplets, which are pairs of 4 integers, such that a plus b plus c plus d is equal to the target. We're looking to find sets of numbers, unique quadruplets. The a, b, c, d are distinct. They can be negative. You want them to the target. Okay. Enter the fourth solution for this is quite bad. So I'm not even going to consider that, but technically you could. Or IJKL. Target minus I, target minus J, target minus K, target minus L. And then if L is there, that's a solution. Kinda not efficient though. There's also a hash map away. So imagine starting at the hmm. I'm not sure how to do this. Array 2 pointers and looks like you really need to sort the array. This is gonna figure out what they're doing with 2 pointers when they sort the array. So that'll be -2. You can kind of track. There's a -2. There's 2 pointers. Repeated values are next to each other and skips. Free sum. Yeah, that's true. If it's been cubed, you can do the hash map. Let's first sort it. Okay. We're running a generic function ksum. That sounds good. For ksum. Reference to noms. Noms. Target. Start. And then we're recursively. Here from ksum. Is a vector. Int. And a vector int reference. Noms. Target. Start. Here. See if there's a YouTube.
We solved the original 2-sum problem. We also solved 2-sum 2, and then we solved 3-sum. I definitely recommend solving these two problems before you solve this one because this problem is pretty much exactly like the 3-sum problem, with just a single extra for loop. But that way is kind of the naive way to approach this problem, because yes, this is literally just 3sum with one extra value. And if you're not familiar with those problems, let's just kind of skim through this description. We're given an array of integers. We want to return all the unique quadruplets, so 4 values A, B, C, D, such that these values are at 4 separate indexes in the input array, and these 4 values summed together equal the target value, which is a parameter that we're given. So the 3sum problem is pretty much exactly like this, except instead of 4 values, we're required to find 3 values. So the first thing to understand is that we want unique quadruplets. We don't want duplicates. How do we eliminate duplicates? Because suppose we had, let's just look at a very simple example, target 8, and we had 5 input values and all of them are 2. So suppose, we had a bunch of for loops. We say, okay, this is the first value, this is the second, this is the third, this is the fourth. Okay, these sum together equal 8. So we found one solution, right? Next, we might try something like this, right? Like literally the same exact values, which sum up to 8. Now, technically they are at different indexes. So does this count as a different quadruplet? Well, it does not, because each quadruplet has to be unique. That's one of the requirements. So how do we eliminate that? Well, let's actually look at a slightly different example. And let's say, we don't necessarily have 4 values, but we have some amount of values that we're required to do. And just to make it simple, let's say we were looking for 2 values that sum up to some target, and we want unique results, right? So suppose we looked at the first value and then the second value. Okay, 2 plus 3. Let's say this was the solution, right? So we'd say, okay, with this pointer, we're saying, okay, the first value in our pair of values is going to be 2. Then our next pointer is going to look at 3, okay? So we found one solution. Next, our second pointer is going to go here, and then same 3. So we found another solution. Nope, we don't want duplicates. So what we're going to do with the second pointer is increment it, but we're going to keep incrementing it until it lands at a new value. If it's the same as the previous value, we don't want to consider that as a solution. So the way to do this, though, is to sort the input array so that all duplicates are next to each other. So you don't have to keep track of which ones that we've already seen before. You don't really need to use some kind of data structure for that. By sorting the input array, we can kind of detect those duplicates by themselves. And that's really the main thing about this problem, to sort it and then not have duplicates. And once, in this case, we have 4 values that we're looking for. And then, if we choose the first one, we'll be looking for 3 values. If we choose the second one, we'll only be looking for 2 values. Once we get to the point where we're only looking for 2 values, it's basically boils down to the problem 2sum2, which we've solved on this channel. I recommend checking it out if you're not familiar with it, but it's basically that when you have a sorted input array like this one and you're looking for some target, let's say in this case, the target is equal to 3. Let's scribble this stuff out because we don't need it anymore, but we're looking for a target of 3. This is our subarray. Our left pointer would be over here. Our right pointer would be over here. We're going to look at what does this currently sum up to. 1 plus 3 is 4. So we want a smaller sum. Right? Since we want a smaller sum and we know that this input is sorted, that means we should probably decrement our right pointer. Because if we increment the left pointer, we're going to get a larger value, which is going to lead to a larger sum. But we want a smaller sum, so we're going to decrement our right pointer, and then we'll end up getting a smaller sum. So in this case, we have 1 plus 2, which is the target value. So I'm not going super in depth here because this is actually its own LeetCode problem, which is 2sum2. But that's pretty much the idea we're going to use. So, if we were doing this with for loops, we would have one for loop to get the first value, and then we'd have another inner for loop to get the second value, and then we'd have a while loop, a third while loop, with our left and right pointers, while our left pointer is less than the right pointer. And then we basically do that whole 2-pointer technique that I just showed a second ago. So in total, and by the way, this while loop is going to be determining 2 values for us, the left and right values. So in total, we have 3 loops. So the time complexity for this solution is going to be n cubed. Even though we sorted the input, that's really not the bottleneck. The bottleneck is the fact that we have literally 3 loops over here. So this is a perfectly valid solution. It's just one extra loop compared to the 3sum problem. But what this problem is really getting at, and I wish they actually explicitly stated this rather than just calling this 4sum, it's about, a generic solution. Because in this case, they gave us 4sum, but they could have given us 5sum. We're looking for 5 values. Or what if we were looking for 6 values or 7? Or even a variable amount like k. Then we would need to, keep making loops for however many k values that they gave us, right? That would be pretty hard to code up. Can we create a generic solution to solve this problem? And yes, we can. It's pretty much the exact same idea as the for loop stuff, except we're going to be keeping track of a variable. In this case, the k is going to be 4, right? Because we're looking for 4 values. And instead of just creating for loops like this, we're going to use recursion, which is basically going to be simulating those for loops, right? So basically, let's say k is equal to 4. Well, we're going to call our recursive function, find, the first value, right? We're going to find a, and then we're going to call our recursive function and basically pass in k equals 3 now. Then we're going to find our second value, which is b. Then we're going to call our recursive function again, which is going to pass in. Now we're looking for only 2 more values. Once we get to 2 values, that's pretty much our base case. That's pretty much that while loop I was talking about, while left is less than right, which is the 2-pointer technique. And then, we're going to find all the solutions that exist with whatever subarray that we're given. So that's pretty much the idea. But obviously, as you can see, this solution will work on not just a 4 sum, but any pretty much variable amount of sums that we're looking for. So that's the idea. Time complexity, even with recursion, is still going to be n cubed. So now let's code it up. Okay, so now let's code it up. And like I said, first the important thing to eliminate duplicates we want to do is to sort the input. And then what we're going to do is declare a couple of variables that we're going to use in our recursive solution. So one is the result, which is initially going to be an empty list. It's going to basically contain all the quadruplets that we're looking for. And quad is basically short for quadruplet. It's going to maintain what the current quadruplet that we're building is. That's really just a variable that's going to be used within our recursive function, which I guess just to be lazy, I'm going to call helper, but maybe you could call it ksum or something like that. Actually, in fact, let's do that. Let's call it ksum just to be descriptive. So the first variable that we're going to pass in is k, however many values we're allowed to use. Initially, that's going to be 4, but then it's going to be decremented to 3 and to 2, etc. We're also going to pass in the starting index that we're looking at of the input array nums. And lastly, we're going to pass in the target value. Now, I'm not passing in nums because it's, it's going to be accessible within this function anyway. But the reason I'm passing in target, which is also accessible, is because target is actually going to be changing, right? As we pick one value, right? Like so far we have our target, but let's suppose we picked our a value, then we'd subtract a from the target, and then we'd have our new target. And then, we'd also subtract b to find our new target, etc., etc. Okay, so with recursion, we always try to start with our base case. And the base case is pretty much if k was equal to 2. But I'm actually going to rephrase that and say if k was not equal to 2. I wrote it the other way originally, but it turns out to be a lot of like nested loops. So in here, I'm basically going to have our non-base case, which is pretty much going to be us starting our pointer, right? I is our pointer, and we're going to go from the starting index to the end of the input array. We could do until the end of the input array, but just to be a little bit slightly more efficient, we could subtract from this basically k plus 1. The plus 1 is basically because this is non-inclusive in Python, just the way that loops work. But basically what this is doing is saying, okay, let's say k was equal to 4. Okay, well, we're going to start at index probably 0 and then keep iterating throughout the entire input array, except for the last k values, k plus 1 values, right? So in this case, the last 3 values we're not going to touch. The reason is we want there to be at least 3 values for the other positions. Because right now, if k is 4, we're picking the first value. We want at least 3 values to come after it so that those can be picked and we can actually form a quadruplet. Okay, so what we would do then is call our helper, right? This nums of I is a candidate. We're going to call our helper. We're going to decrement k from it. We found 1 value. So now we're looking for k minus 1 values. The next starting index should be I plus 1 that the next value starts at. And the target should be target minus nums of I. So that's very simple. Before we call that helper, though, we should probably add or update our quadruplet. So append to the quadruplet nums of I. After we're done with that helper, though, we're going to clean up this call and basically pop from our quad that last value that we just added. Now there's only one problem here. Suppose we had an array like this, right? So the first value we pick is going to be 1. Okay, then on the next iteration of the loop, we're going to get to the second one, but we don't want to use that same exact value in the same position multiple times because we know that can lead to duplicates. So we don't want to get those duplicates. So what we're going to do is say, okay, if nums of I is equal to nums of I minus 1. If it's equal to the previous value, then we're going to continue. We're going to skip this iteration of the loop. But what if we're looking at the first value? We're looking at the start value. Well, we wouldn't want to execute this then. So what we can say is if I is greater than start and this is the same as the previous value. Then we're going to skip this. We pretty much did all of this. Oh, and by the way, once that for loop exits, we want to return because we don't want to end up executing this portion of the code, which is going to be our real base case, which is literally just 2 sum 2. So if k was equal to 2, which is this case, then we're looking for two values that sum up to whatever target we were passed into this function. So we're going to initialize our left and right pointers. Left is going to be initialized to the start. Right is going to be the length of nums minus 1, basically the last index. And we want to continue while left is less than right, because if they were equal, then they would be pointing at the same exact value, the same index, and we're not allowed to use two values from the same index in a single quadruplet. So there's really three cases here, though, with our two-pointer technique. Either our sum so far, which is nums of left plus nums of right, is less than the target, or it's greater than the target. So I can copy and paste that and change the equality sign. So if it's greater than the target, that's a separate case. And the last is if it's exactly equal to the target. So first, if the current sum was less than the target, we would want to increase it. So to increase it, we can increment our left pointer, because remember, even this subarray is going to be in sorted order. If it's the opposite case, that means our sum is too big.
This is
We want it
freaking...
to get smaller, so we
Not
decrement
bro.
the right pointer. Lastly, we have found the exact sum that we're looking for, so we want to append to the result whatever quad happens to be, plus these two values, nums of left and nums of right. There's multiple ways to do this depending on your language. In Python, we can actually just add two lists together. So this quad right now is going to have the first two values. We want to add to it two more values, which are nums of left and nums of right. So we're pretty much just adding two lists together here. So these are the four values, which are going to form a single list, and that list is being appended to the result list. Okay, but we're not done yet though, because if we leave it like this, it's going to execute the same loop, and it's just going to get caught in an infinite loop. We want to still update our left and right pointers. Now, it doesn't really matter which pointer we update in this case, because we know both of them are going to have to be updated, because otherwise they would end up being a duplicate. But we're just going to arbitrarily choose the left pointer to increment. So what I'm going to do is increment the left pointer at least once. But if it happened to be that the left pointer didn't change, basically nums of left is still equal to nums of left minus 1, then we want to keep incrementing it, right? Because we don't want it to be the same value it originally was, because that's going to result in us appending duplicates. But there's one thing, we don't also want left to go out of bounds. So before we check this, let's make sure that left is less than right. And by the way, if it did cross the right pointer, this loop would exit, and then we'd go back up here, and then this loop would also exit. Okay, so a lot of code. And this is definitely really complicated if you haven't solved 2-sum 2 before or 3-sum, but if you have, this actually isn't as difficult as it might look. So that pretty much is the entire code. Let's actually call our recursive function though. So we can call ksum, passing in 4 as the k value. The starting index is going to be 0, and the target is going to be the original target we were passed into this function. After we call that, we know that our result list will be updated, and then we can return that result. Okay, now let's run the code to make sure that it works. Whoops, it's just like me to have stupid mistakes here. So I forgot the colon, which is required after a function declaration. Okay, and once again, I don't know why I called this helper. That's what we were originally trying to call it, but let's change it back to ksum. Okay, now it finally works. As you can see on the left, it's pretty efficient, so I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon, where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.
Oh my god.
welcome back to my C++ series. So today we're going to be talking all about timing. So how do we time how long it takes for us to complete a certain operation or execute certain code? That is what today's video is going to be about. Now, timing is useful for so many things, whether or not you want something to happen at a certain time, or if you're just kind of evaluating your performance or benchmarking and seeing how fast your code runs, you need to know how much time passes while your application is actually running. There are several ways to achieve this. Since C++11 we have something called Chrono. It's essentially part of the library that comes with C++, and it's not something that we actually have to go to the operating system library to actually do. Before, if you wanted a high resolution timer, meaning you wanted a very, very precise timer, you need to actually use the operating system's library. So in Windows, for example, we have something called Query Performance Counter. We can still use that stuff, and in fact, if you want a little bit more control of how you actually access that timing capability of your CPU, then you probably do want to use the platform-specific libraries. However, today we're just going to be taking a look at the kind of platform-independent C++ standard library way of figuring out how long or how much time passes between our lines of code as they get executed. And that is part of the Chrono library. Now, I've linked a link in the description below to the actual CPP reference for this Chrono kind of API. I'm going to show you a very simple way of how we can set it up and start using it here so that we can figure out how long it takes us to run certain code. And I'll probably also show you one way in which it can be useful. Now, this whole video is going to be important for the future of this series because as we start integrating more kind of complex features and I start talking more and more about how to do things properly and how to write good performing code, we're going to be using timing to see that difference. So if I show you a kind of slow way of doing things and then I say, well, actually, it would be better if we did it this way, you'll be able to actually see the difference in terms of how long it takes to actually run that code. So this is very important. From this, we'll probably branch into benchmarking, and I'll talk more about benchmarking in another video, and we can set up some kind of API so that we can time how long it takes to complete functions and arbitrary scopes of code probably as well. So yeah, pay attention to this video. Let's jump right into it and learn how we can time our code. So the first thing I'm going to do here is include Chrono. This contains pretty much everything we need. I'm also going to include Thread because we'll do some stuff with that in a minute as well. So from Chrono, it's very, very simple to actually use that library and figure out what the current time is. We can just type in std chrono high resolution clock and then now. This is what actually gives us the current time. If you hover over this, you can see it returns a time point of std chrono steady clock. It's quite a long type, which is why I'm just going to use auto and kind of label this as the starting time. We're then going to execute some kind of code here. What I'm going to do for now, because I don't actually have any other code to execute so that we can time, I'm just going to write std this thread sleep 4, and then we'll just write 1s for 1 second. And to get that, we'll actually have to use in namespace std literals and chrono literals to get that s there. Okay, cool. So basically what we're doing now is we're telling this current thread to sleep for 1 second. So we're saying just kind of pause execution for 1 second. So obviously by writing this code, when we have our start and our end timing, we should see it be around 1 second. It probably won't be exactly 1 second because first of all, thread sleeps are not guaranteed to be exactly how much you tell it to sleep for, but also there'll be overhead from the actual timing. So if we get back into this, I'll write auto end, and this will be exactly the same as this start code here. And finally, we want to figure out the actual duration. So I'll write std chrono duration. Well, we can just get this in floats. That'll be high enough resolution for us. I'll call this duration, and it will just be end minus start, just like that. We could have used auto here as well, but this type isn't quite as long, so it's fine to write it out. And finally, I'm just going to see out that into the console. Duration.count. End line, and this will be in seconds, so I'll just add s to the end of that so that's clear. And if I hit F5, you can see the number we get here is pretty much around 1 second. So that's it. What I just showed you is a platform independent way of actually figuring out how long something takes or how much time passes or getting the current time and all that. This Chrono library is fantastic. It's very high resolution timing and it works on pretty much all platforms. So really I recommend that you use this for all of your timing needs unless you're specifically doing some kind of low level thing so you want to reduce overhead even more. If you're running a huge game engine or some kind of core library, you might want to use the platform specific libraries such as the Win32 API with the query performance counter and stuff. We might look into that in the future, but really there's pretty much no need for 99% of cases. Just use std chrono. Now, if we dive back into this, I'm going to show you a bit of a smarter way of actually dealing with this because you can see that this is quite a lot of code that we have to run. So suppose that we have a function, I'll call it function, and it does something. Like maybe it just prints, I don't know, hello to the console a bunch of times. So I'll just wrap this in a for loop, and I'll say maybe it does that about 100 times or something like that, right? So we have a for loop, it runs 100 times. We want to figure out, well, how long is this cout operation really? How long does it take cout to actually write stuff out to the console 100 times? I want to time this function. So what I could do at this point is copy start and end and do all of that stuff. That's a lot of work. I don't really want to do that. So instead, I'm actually going to set up a very, very basic struct or class, doesn't matter, I'll just make this a struct, called timer. And this will actually do everything for me. And what I'm going to do here is I'm going to use the whole object lifetime kind of paradigm to actually get it to basically automatically time everything for me. If you guys haven't checked out the video on object lifetime in C++, definitely do that. It's very, very useful. And in fact, this example, I'm pretty sure I did actually give in that video as well. So jumping back into our code, the constructor is going to actually start the timer. So I'm going to grab this and put it in here. Unfortunately, we can't actually use auto, so I'm going to have to figure out what the type is, which is std chrono time point, std chrono steady clock. So std chrono time point, std chrono steady clock. So that's our kind of start. Just call this start and put it up here. So we have our start and our end. And I'll also grab this from here, our duration, and put this in as the duration. Start, I'm going to assign to this in the constructor, and in the destructor, I'm going to copy this whole chunk of code here. In the destructor, what I'm actually going to do is write end equals the same thing. And then finally duration. And I mean, you don't really have to store end, as you can see, because we're really just after the duration. But in case people want to access that, maybe I want to kind of write that into my timer struct. So duration equals end minus start. And that will give us the duration in seconds, of course. Okay, and that's really all I need. Let's just make it even easier and say that we actually print the duration. So we'll say timer took, and then I'll write in duration seconds. Now, because this is such a quick operation, we actually might want to print the milliseconds instead. So I will say float ms equals duration.count times 1000, which will give us the value in milliseconds. And I'll change this to be ms and this to be ms. Okay, cool. Sounds pretty good to me. That's pretty much all I need here. And now we have a basic struct that will basically do the timing and even print it out for us automatically. And it will of course do that upon destruction. All we really need to do is just create the object at the beginning of our function, and that's it. So over here in my function, the way I'm going to do this is just type in timer like that. That's all I have to do, and I'm done. This entire scope, this entire function will now be timed. So if I go back and delete all of this crap that I don't care about, I'm just going to call function like that, and we'll hit F5 and see what happens. Okay, cool. So check this out. We get hello printing 100 times to the console, and at the very end, we see that this took 122 milliseconds. Cool. So we now know how long our code actually takes. 122 milliseconds, very, very slow. Let's see if we might be able to optimize this a little bit. So std endline seems to be quite slow for some reason. So if we just get rid of that and actually put a \n into our print here inside our function, let's see how much faster this will be. And you can see over here that we've cut out about 1/3 of our execution time. Obviously, you should run this a few more times and in release mode if you actually care about benchmarking and all of that, but for now we can still see the difference. Anyway, that is a basic overview of timing in C++ and how you can time your functions and see how long it takes to execute certain code. Obviously. Hey, what's up guys, my name is Jono, welcome back to my C++ series. So today we're going to be talking all about type punning in C++, and type punning is really just a fancy term for just us kind of getting around the type system in C++. So C++ is a strongly typed language, which means that we have a type system. We don't declare everything as auto. I mean, we kind of can because of that keyword, but in other languages like JavaScript, there are no kind of sense of variable types really. And we just have, we don't need to declare a variable type when we create a variable and when we accept it in as parameters into functions or anything like that. We don't have a type system really. But in C++, of course, we do have a type system. We have to declare things as integers or doubles or booleans or structs or classes, all of that stuff when we actually create variables. However, this type system is not really enforced as strongly as it is in other languages such as Java, where it's really hard to get around types, and even C#, where you can do it, but it's a bit more work. In C++, whilst types are kind of enforced by the compiler, you can directly access memory, which means that you can kind of say that, hang on a minute, I know that at the moment in my code, I've been using this type as, say, an integer, but actually, I'm going to just grab that memory, that same memory, and just treat it as a double now, or as a class, or something like that. And you can just get around the type system really easily. Now, whether or not you should is going to, again, depend on your actual circumstance. In some cases, you absolutely should not circumvent the type system because the type system is there for a reason, and you probably don't want to be playing around with it too much unless you have a good reason. But in other cases, it's totally okay to do that. For example, let's just say we had a class and we wanted to write it out as a stream of bytes. Well, instead of kind of going through everything, assuming it's like a structure of primitive types and doesn't have pointers to other places in memory, we can just kind of reinterpret that entire struct or class or whatever we have as just a byte array and just write that out or stream it somewhere, right? We don't have to even care about what types are in it. As long as we know the size, we can just get the data, access it, and then just put it somewhere. So in a lot of cases, it is really useful, and it means that it's kind of that raw, I guess, low-level access that is why I really like C++. And why C++ is so effective in applications where performance is required. Anyway, enough talking, let's just dive in and take a look at a few examples. This is something that I use quite often, so you'll probably see it in other videos, and especially like in the OpenGL series and the Game Engine series and all that, so you'll see plenty of this. This is just going to be a basic overview, but let's just dive in and see what we can do. Okay, so in that first example, I kind of declared an integer, well, I just said that I had an integer, and then I just wanted to treat it as a double. Well, of course, in this case, that's probably going to result in a pretty weird-looking double and not something that you want to do, but again, just to demonstrate how this works, I'll show you anyway. We're going to make a double, we're going to call it value, and we're going to set it equal to a. That's kind of step one. Now, first of all, you can see it works, right? Everything seems to work fine. If we were to print this out, like this, and I'll even put a breakpoint over here, hit F5, you can see what we get is 50. Okay, interesting, reasonable, I guess. I mean, it converted our integer into a double now, so it's 50. Let's take a look at the memory. So I'll go debug, Windows, memory, and memory 1. I'm going to go to the memory address of A and take a look at what is in there. Okay, cool. 32000000. Okay, makes sense. 32 is 50 in hexadecimal. Now let's take a look at the memory address of value. Now, first of all, it's going to have a different memory address. The second of all, well, we know how many bytes it is. It's 8 bytes. Look at that. It's completely different. I mean, 49 and 40 over here, and like what's going on? It's not the same memory at all. Because what it's actually done is it's just actually done a conversion. It's converted an int into a double, because that's what happens if you do something like this. Now in this case, it was an implicit conversion. I mean, we didn't actually tell it to convert anything. If we wanted to be explicit, we could write double A like that, which is fine. I mean, it does exactly the same thing in this case. We don't have to write double here because it will do an implicit conversion, but if we wanted to be explicit, this is actually what's happening. It's converting that A from being an integer into an actual double. Now, what if we wanted to just take that existing memory? We saw 32 and then 000000 in our memory. I want to take that same memory, but I just want that memory to be treated as a double. How do I do that? Well, the first thing to do that we need to do, there are a few ways actually, but this is the kind of raw way, I guess. We take the memory address of A, and then we cast that to a double pointer. So, and a double, by double pointer, I mean obviously a double pointer, not 2 pointers. Now, this part here is of course just taking the memory address of A, so this gives us an integer pointer, and then we're converting that int pointer into a double pointer, and then we obviously need to get back to having a double. So how do we go from pointer to the actual type? We dereference it, and that's what we get. So this looks a bit weird maybe if it's the first time you've seen it, but essentially what we're doing here is we're type punning our integer into a double. So if we hit F5 now, let's see what we get. Okay, so it's a pretty weird looking double. I mean, it's negative 9.2 E plus 61, so yeah, whatever. Clearly not something that we probably want to do, but again, it's just an example. If we take a look at the memory address of A, you can see that of course it has 32, like that. And if we take the memory address of B, of value, you can see what we have over here. Now, what you'll also see is, if you remember that we have 8 bytes of double, the rest is uninitialized memory. Because what we've done here is something pretty bad, because these are different sizes, right? I mean, we've taken a 4-byte integer and kind of assigned it to a double. So what that's done, since we've converted an int pointer into a double pointer and then dereferenced it, that's actually gone ahead and looked 4 bytes past our integer and grabbed that memory, which is not our memory. It's not the memory we have for integer. So this is very bad, and it could even cause a crash in some circumstances. Definitely not something you want to do. I mean, we've copied that memory into a new double value block, so that's safe. So we haven't written and we can't at this point, even if we do write to value, we're not going to be writing to memory that's not ours, but we definitely have read from memory that's not ours, so that's not good. Let's take a look at a more practical example. So what I'm going to do, now of course if you didn't want to, just a quick note, if you didn't want to actually create a whole new variable and you just wanted to access this int as if it was a double, then you could just add an ampersand to the end of this double here, which will just reference it and not copy it into a whole new variable, and that way you will be actually editing this integer memory. So that is dangerous, because if I decide to write something like 0 into here, then guess what? It's actually going to write 8 bytes instead of 4, but we only have space for 4, and this might even crash. So let's take a look at a more practical example. What if I have a struct called entity, and this has two variables, int x, y. Now we know, or at least I hope you know, that if we have, let's just initialize this to 5 and 8. If we have something like this in memory, then really all that struct is like it is made up of those two integers. It is literally those two integers, and that's it. If we look at its memory, you can see we have 5 and 8. That's it. The struct itself does not contain any kind of padding, any kind of data, whatever. If it's an empty struct, then it has to be at least 1 byte. So there will be something in there because we need to be able to address that memory, and we can't address it if it's not there. So we have to have at least 1 byte in a struct, even if it is empty. But if we have variables in there, like in x and y, that struct is just 2 integers. That's all it is. There's no like extra data that says, oh, this is an entity struct. It's not how any of that works. It's just the 2 integers. So what we can do here is we can actually just treat this entity struct as an int array, or maybe just extract one of its integers by not even doing e.x or e.y. Let's take a look. So I could just say e.x, and that would give me my x variable. But what I could do also is just say, well, let's make an array out of it. So this will be a raw array. I'll say int pointer, and I'll call this, I don't know, position equals the memory address of e, and then just cast that to an int pointer, like that. And now if I wanted to print this out, I'll just write stdc out, position 0, and then comma, position 1, like that, as if it was just an array. And you can see there I have it, 5, 8. I mean, I'm accessing it like it was an array because I've converted it into an array, basically. I've said that this entity memory address contains the beginning of an int array, right? Or it just contains a pointer to an integer. And then I've just looked 1 integer ahead. Using the same kind of method, what I could do is something even crazier, perhaps. Let's just say I wanted to get that y variable out of it. Now, of course, any sane person would just write that. In fact, that's probably what I would write as well. I mean, I guess I'm pretty sane. But what you could do is you could get the memory address of e, like that, convert it into maybe like a char pointer. Again, not sure why you would, but let's just say that you did. That is, of course, 1 byte in size. So we need to go 4 bytes forward like that, and then convert that memory into an int pointer, and then dereference that. And then we have access to y. So let's go ahead and print this crazy piece of code like that and hit F5. Oh, check that out. We get 8, which is, of course, the y position of the entity. But the point is, what we've done here is we've just kind of just reverted to raw memory operations, something that C++ does really well, which is why it's such a powerful language. One of the big reasons why it is such a powerful language, because it has that kind of, it can manipulate memory really easily and really freely. And memory is by far one of the biggest things we actually have to deal with when we're actually programming. So whilst this code probably should never exist, like in real applications, because it's crazy, and of course in this case you can just use e.y, it can be very useful if you don't want to deal with kind of copying or conversions. Because again, if we wanted this as an array, well, we can't, like, if you, let's just say you wanted to create, you know, I don't know, get positions or whatever as an int array, well, how would you do that? Well, I mean, I guess like what you would have to kind of do is, well, this is not an array, so I'd have to just create like a new int array, right? Now, because this is in a function, and you know, we're not taking in like some kind of memory to put that array into, we probably need to create our own array, which means we need to heap allocate it and then copy that. And I don't even want to write this code. It's disgusting. It's terribly slow. It's awful. What I could do instead is just return, well, I don't know, memory address of x, right? Now this, of course, really depends on the user not trying to do something like position 2, because there is no third element and that's going to go way past the memory. However, you can see that now what I have access to, if I call e.getPositions, is an actual int array with 2 elements in it that I can access. And I can also write to it, so I can say position 0 equals 2, and I've changed the x coordinate of my entity, but also I haven't copied anything. I haven't copied memory redundantly. I'm just linking to the same memory. I'm just choosing a different way to actually interpret that memory. If you don't want to deal with raw casts, you can use reinterpret casts to do exactly the same thing. We will have a video for C++ casts in the future. The reason I haven't done one yet is because I don't use them too often. I just use C-style casts most of the time. I probably should use C++ style casts, but what are you going to do? Anyway, that is basically type hunting. It's just us being able to say, I'm going to treat this memory I have as a different type that it actually is. And you can see we can do that really freely. All we really need to do is just get that type as a pointer, and then cast it to a different pointer. And then we can dereference it if we need to, and just deal with it. Anyway, I hope you guys enjoyed this video. If you did, please hit the like button. Let me know what you think about type hunting and this type system, and why type hunting is useful and why you love it so much, or you hate it. I don't know exactly how you feel about it. Leave your thoughts in the comment section below. If you want to support the series, please go to patreon.com/thecherno. Huge shout out, as always, to all my lovely supporters. This series would not be
Casual 10-hour stream. Yeah, casual 10-hour stream. I feel like it was not that long, but I guess it was. Oh, yeah, I'm getting off. I'll still do some work for the next few hours. Or take a shower. Yeah, see you guys.